Am I on stream?
Yes.
Okay, hello everyone. Welcome to this, the third edition of the WebAssembly workshop, Betraying Popple, by appearing now in ICFP Splash. So thank you for all coming. Our first speaker is going to be Andreas Rosberg, who almost needs no introduction at this point, and he is going to be giving us a talk on spec tech as well as a practical demo. So please take it away.
Yeah, okay, thank you. So first, what's new in WebAssembly land? So some of you might not have heard yet, but as of a month ago, version 3 is released. So pretty substantial release, much bigger than the 2.0 release we had before. So with new features that have been in the making for, I think, almost since the beginning, actually. So for 8 years, like things like garbage collection. We now have low-level support for garbage collection. We have support for exception handling. And finally, for the first time on the web, we managed to get it in tail calls. Right, and there are other things like 64-bit address space, so you can now build much bigger applications. There's the gap we filled in the design with multiple memories, and there are a whole bunch of other goodies. But this talk is not going to be about that. This talk is going to be about specifications. Oh yeah, but I should mention, all that has been shipping in browsers already some of that years ago. So it's all there right now in all the engines and browsers, and it's ready to be used. So you can target it right now as we speak. Okay, but that's not what the talk is about. The talk is about specification, the specification of WebAssembly. So one of the features of WebAssembly that sets it apart from other mainstream industrial programming language technologies is that it's fully formalized, right? And I always have to explain what I mean by fully here. By fully, I really mean end to end. So from the first byte of the binary format to the last bit of what happens at runtime. And what we're using to do that is really like a textbook formalism, like you would see in every second paper on a conference like this. So we really try to do not anything fancy or new but to show that these techniques are sufficient for handling WebAssembly. And the other interesting part here is that this formalization is not just something we did on the side, it's a central part of the language standard. It's a normative part of the language standard. And in fact, the whole specification is centered around the formal semantics. So that's, again, pretty different from any other major language technology. So here's a peek of what it looks like. This is a page from the spec that shows the execution semantics of a couple of instructions. I won't go through all of that, but there are a couple of things to see here. So one is we have the formalism, which is small step reduction rules. So this would be, for example, for the BR-if instruction, which conditional branch essentially. But we also have, so that's all like should be familiar to this kind of audience. But of course, we have a much larger audience for a document like that. And most of the compiler writers, for example, they are not that familiar with that. They want to read some prose. So we also have the prose specification, which is supposed to express the same thing. So there are these two formulations. One is the formalism, which is sort of declarative. And then there is the prose, which is more algorithmic. It's defined in terms of like pushing and popping values to some stack machine. It's obviously a bit more hand-wavy. And they're supposed to be equivalent. And in case they are not, then that would be a spec bug, right? So they're both normative in that sense. Similarly for validation, which is our term for type checking, or what the JVM would call bytecode verification, that's just typing rules. And again, they're pretty nice inference rules like you would expect from a decent paper, but also equivalent prose that kind of spells out the conditions as text, as stylized English text. But it's not just that we have a formalization, we also have a mechanization. So meaning that we have fully machine verified soundness proofs for all these, for the semantics. And again, this is not just for an idealized subset, it's for the full language as specified, right? And this is thanks to people like Conrad and others on the WebAssembly team who did all the work for that. So there are actually two mechanizations. One is in Cork and one is in Isabelle. And currently that is handling WASM 2, but there's ongoing work to extend it to WASM 3. So another kind of unique feature about WebAssembly then is I think it's the only low-level language that has a completely specified semantics and absolutely zero undefined behavior, right? Thanks to all that, among other things. So, and that allowed us to put like these nice theorems into the actual language standard that we have soundness, like the typical syntactic soundness theorem about progress and preservation. So this is an actual part of the spec, some appendix in the spec. So why do we care about this? Well, I guess, again, I'm kind of preaching to the choir with this audience, I would hope anyway. But let me reiterate anyway why we care about formalization. So one obvious advantage is it gives you higher precision about what's going on, right? With most of the mainstream language specifications, it's a combination of prose and wishful thinking, essentially. And when you do it in a formal way, there is no way to take shortcuts. You really have to spell out all the details. And that, of course, also is leading to, hopefully, a more correct specification, especially when you actually do proofs about it, right, like we do. So you have much higher assurance that what we are designing and defining here actually makes sense. And then there is the other thing for people, at least, who are versed in this kind of notation. It's also a much more efficient way to communicate, right? You saw in some of the rules, like for BR-if, there were like two-line simple rules, and the prose was like this. There are actually worse examples. So it's a much more effective and concise way of conveying what's going on with much less boilerplate. And then there's a last kind of advantage, which is often overlooked, that it also has an impact on the design itself. So when you design a language with formalization in mind from the beginning, then this creates a very important feedback loop. And it forces you as a designer to stay honest, right? You can't cheat anymore. So when you design a feature and you have to formalize it, it turns out the formalization gets really complicated, or you design a new feature and you see that it doesn't fit what you had so far quite well, then chances are there's something wrong with your design. I mean, not always, right? There can be cases where it's justified, but as a rule of thumb, if the formalization is difficult or complicated, then you might want to consider rethinking the design. And I would argue with WebAssembly, it has led to a simpler design or cleaner design in some cases. Okay, so this is all great. Oh, I should mention one more thing, of course. What we're doing here is we're standing on the shoulder of giants, right? So I cannot give a talk at an event like this, like ICFP, without mentioning these giants. And that's, in particular, this book, The Definition of Standard ML. This is from 1990. That was the first general purpose language that was fully formalized in its definition. So this is what it looked inside. It only had these rules. It was a work of elegance and beauty. It completely blew me away as an undergrad when I first encountered this, and I thought this is what everybody should be doing because it's so obviously better than everything else. Ours doesn't look quite as nice. We have all this nasty prose in between. Right, and they also didn't stop there. A few years later, they also managed to mechanize all that, so there has been follow-up work. So this was the first language that was fully formalized and also fully mechanized. And we're kind of taking that achievement and putting it into the mainstream, if you want. Okay, so this all sounds great, but there are some problems here. One is WebAssembly is large, right? So with WebAssembly 3 now, we have hit the 500 instruction limit, or not limit, but like more than half. More than half of this is vector instructions, which is a whole zoo of like, yeah, annoying, irregular things. But even without that, you would have a problem, right? We also added a non-trivial type system. So the type system of WebAssembly used to be really trivial. You just had these 4 base types and that's it, right? Now with GC in particular and reference types more generally speaking, we have structural record types, function types. We have type recursion between them. We have co-contravariant subtyping and all these things, so it's no longer trivial. So this is the table of contents from the spec, and you can see it's around 240 pages at this point, plus another 80 pages of appendix, which contains, for example, these type soundness developments and stuff like that. So it's a lot of stuff. And it's not stopping there either, it's still growing fast, right? So there are still substantial features missing. We merged about 20 proposals since we started with WebAssembly, from fairly small to very large, but there are still as many still out there. Probably not, well, there's still a few big ones out there. So I guess the two important ones from my perspective, your mileage may vary, is that are not in there yet. One is threads, including the whole like relaxed memory model issue. And the other is what we call stack switching, so continuations essentially. From my perspective, those are the two biggies, but there are lots of others as well. So this is not like a solved problem. We have done all the work and now we can party or something. No, this is going to get back to us all the time. So, and to understand why that is a problem, well, how is the spec written? Well, actually the formalization that was written first, that was, for the original version, I wrote that it only took a few days actually to get the core of that right. And then it took more than a couple of months to actually write the entire prose, right? Because that is so much more tedious. So it's basically a handcrafted translation into stylized English. And as you can imagine, that's tedious and also very error prone. And it's also, the whole document is written in some markup tools called Sphinx, and it has all this embedded LaTeX, and you can't use any macros, so it's like really terrible. And all this kind of duplicate work of writing both these formulations, of course, has to be repeated with every proposal. And it's not just writing this stuff, we also have a process of code reviews, right? So our spec sources are on GitHub in the open, and when a proposal is written or being merged, then the editor, which usually is me, has to review all these changes, right? And because, like, I don't know, have you ever reviewed LaTeX code? That's basically write-only code, right? And some of the diffs are extremely large. So that was the biggest one, was the vector instructions. When we added them first, that was more than 20,000 lines of code added to the spec sources, just the spec sources. Plus, I don't know, 80,000 lines of tests, actually. And that, again, is just speaking about the document and its sources. And then there's the mechanization, which is a whole yet different story. So again, somebody has to sit down and hand translate all these manually written paper formalism into something that proof assistant would understand, something like Hawk. And as a result, they obviously are challenged to keep up, right? So there's obviously is a problem here. It's sort of an engineering problem, like how do we make this scale? And it's not like we're surprised by this. It was kind of obvious when we started that we would run into this eventually. But
have stream audio now? Yes. Okay.
Okay. Oh yeah. Right. So I probably won't have time to go into the fourth part, which is the concrete syntax. That is also not overly interesting, but I want to go through the first three parts a little bit. So I said we have to start with abstract syntax, right? That is the core of anything you want to formulate. So in SpecTech, you can define abstract syntax by syntax definitions. So let's say, for example, oh yeah, sure, absolutely. Thanks for. There's quite some delay. Oh, that may be a bit too much, but okay. Okay, let's say for the types, so WebAssembly has this notion called value types, which are the types of primitive values. For this demonstration, let's keep it very simple. So say we just have two, which is I32 and I64. All right, so that would be your abstract syntax for value types. That is quite boring, but you can see how to read that. I guess I don't have to explain that, right? It's the alternative of two things. Let's look at instructions. Let's take a tiny instruction set with a couple of instructions. Let's start with the most important one, the knob. That's the instruction doing nothing. Then another simple one, let's say drop. That's the instruction that just drops some operand from the stack on the floor. Slightly more interesting would be something like select. Whoops. So that is kind of like a conditional, but an ego one. So it takes three operands, and the last one being an integer that decides which one of the other two to pick. We want the actual values themselves, so we have to have some notion of constant. So in WebAssembly, we have the const instruction, which allows you to push a value. And that has two immediates now. One is the value type of the constant you want to push, and one is the constant itself. So these are now other pieces of syntax I have to define. I already defined value types, but now I have to define what a constant is. And for the purpose of this demonstration, I want to keep it really simply and say these are just natural numbers. So nat is a built-in type in SpecTech. And in SpecTech, you have to kind of write these sort of like data types. So they have to usually start with the constructor. That is not quite the syntax that WebAssembly itself is using. So we can give SpecTech some hints for how it should render this when it's printed, right? So we can say something like this. That would say that when you see a const constructor with the two arguments rendered like this, and that is the actual WebAssembly syntax that we usually use. Okay, this is slightly too large. Okay, maybe two more instructions to deal with locals. So we have local get, which takes a local index as an immediate, and local set similarly. So locals are just indexed by numbers, so we again have to define what a local index is, and that for now we just say again it's just a natural number. In reality it's bounded to 32 bits, but let's not be too pedantic about it here. So for this demonstration, let's say that's WebAssembly. Okay, very, very small and tiny, but good enough. So that's our abstract syntax for that. Maybe let me check whether that. Okay, so SpecTech doesn't complain. I didn't make a mistake so far. So let's move on to validation. Can't type. Validation. It's not that hard, man. So we have to define typing rules. So, and these typing rules, they form a relation, right? Basically. So the feature that WebAssembly has, the SpecTech has here to do this kind of things is defining a relation. So I declare a relation, say I have to give it a name. So this is the relation that types instructions. So let's call it instruction OK. And I have to spell out the shape of this relation and the notation I want to use for it. And in the simplest case, it would be just assigning an instruction type, I go back to that in a minute, to an instruction. for various practical reasons, we want to be a bit more general and have the relation assign instruction types to instruction sequences. So instruction type is, again, just a piece of abstract syntax we have to define. And that is, we have a stack machine, so every instruction is characterized by what it pops from the stack and what it pushes from the stack. So it's essentially a function, or a combinator, really, if you're a functional programmer. So an instruction type is essentially going from a list of inputs to a list of outputs. So the list of things it pops to the list of things it pushes back to the stack. And I can write this cleany star here is the notation for lists. We can also use question marks or pluses here, which is sometimes convenient, but I think this is hopefully self-explanatory. And the arrow here is just notation that we introduced. That's just user-defined notation. So SpecTech has a bunch of these operators built in as a kind of atoms that don't have any semantics, but you can just use them to define syntax. So with this, we can already define some simple typing rules. So a rule now, for every rule, you have to say what relation it belongs to. And then you have to give it like an individual name. So let's start with the rule for knob. We just call it knob. And the knob instruction, now I just have to basically match the pattern of the relation I have defined. None of this should be surprising if you know how type systems work, right? But this is how you write it down. And knob doesn't expect anything on the stack, neither does it push anything. So the sequence is empty. So epsilon is our notation for the empty sequence or the empty list. So that's the type of knob, right? That's the most trivial one. Drop, slightly more interesting. That takes a single argument and doesn't produce anything. And here I'm just writing t as a meta variable for this rule. And of course, SpecTech can figure out from the types I declared now that this has to be a variable that stands for a value type. And there's no constraint on t here, so you can instantiate that rule with any value type you want, and it would always apply to all of them. The next one, what did we have? Select. Slightly more interesting because that has 3 arguments, 3 operands from the stack. So 2 arbitrary values and another one that has to be an I32. That's the condition we're using. And it returns one of the 2 t's, right? And here we're using the same meta variable multiple times, which means they all have to be instantiated with the same type, as you would expect. Next one would be const. Const also has a type here, and it has a constant. And conveniently, we can just read off the type, and it's t. So it's not much we have to do here. Now we're getting to locals. So local get. Well, what's the type of that? It doesn't take anything, so the left-hand side is epsilon. It returns some t, but that's not an arbitrary t, right? So it's the t of the local we have declared. I mean, this language doesn't actually include the declarations for locals, but let's ignore that for now. So assume every local has a given type. So this is where we need a context, right? So we have to be able to look that up. So that's why typing rules really are not just of this naive form we see here, but you usually type under a context, and you use this turnstile notation. This says that this instruction sequence has that type, assuming that typing context. And the typing context is again just a piece of syntax that we can define in SpecTech. And here it's convenient to use one features of the SpecTech meta notation, which are record types. So our context can be a record of different namespaces. For this simple example, we just have one, so it's a bit overkill to use a record, but just to show how that works anyway. And in WebAssembly, it's convenient that all our locals and other namespaces too, they are always just indexed by natural numbers. So we can represent the typing environment just as a sequence of the types of these things. We don't even need a map for that, right? It's just that is the types associated with all the indices. So having that, we now need to adjust our rules here so they all actually take that context. So I was lazy before not doing that. I also have to instruct SPECTAC that uppercase T, which would otherwise syntactically be parsed as a constructor kind of thing, is to be treated as a variable of a specific type. And now we can formulate this rule and give it a side condition. So you write side conditions sort of upside down from inference rules, using a double dash, and then you can have a Boolean side condition writing if. And in this case, we will want to look up the type of X in C, so we can take the field of that record and index into it, and that gives us our T. So that's all there is to that. And local set is almost the same, except that the direction here switches around. Okay? And finally, you need rules for sequencing instructions. So this is individual instructions, but I said that the relation is supposed to type sequences of instructions. So how do I do that? Well, there are multiple ways to formulate it, but let's do the symmetric way. So if I have two sequences of instructions, and I can use these underscore numbers like in LaTeX to distinguish them, then they have a type T1 star to some T2 star, provided, and now there's the recursive case or the inductive case, so we inductively apply the same relation, so we have to write it like this. The premise here is apply the same relation to either part, right? So if that has the type T1 star to some intermediate thing, T star, and similarly T2 star goes to, T star goes to T2 star. Then we can just plug them together, and that's, everything should be what you expect, right? Nothing fancy going on here. And then we also need to be able to type the empty sequence. That is sort of trivial. That's just this. Okay. There's one more rule you actually need to have, which is sort of weakening rule, but I will skip that. And rather, in the interest of time, go to execution. So as I mentioned briefly before, our execution is defined in terms of small step reduction rules. So rules that tell you how to take a single step on a sequence of instructions and go to a new state that has one step less work to do. And again, we can define that using a relation. So let's call that the step relation. And the step relation takes a sequence of, in the simplest form, a sequence of instructions and maps it to a new sequence of instructions, a simpler one. And the idea for execution is that you apply that over and over until the instruction you have arrived at is in some sort of normal form, and the normal form is being that all the instructions are values. So with expression languages, you usually do that. You have your constants as a subset of your expressions. Those are the values. And we can do something very similar for WebAssembly. So we can define the syntax of values as just the const instructions. And SPECTAC will realize that this is a subset of the full instruction syntax we defined earlier here, which had this as just one case. So essentially, your program has terminated when you've reduced to a form where all the instructions here are just values. That's your resulting stack, essentially. There's one more thing. This is not actually enough because we also have locals, which are a form of state that we have to look up. So really what we are reducing is not just the instruction sequence, but we have a so-called configuration, which is a pair of some state and an instruction sequence. And again, the semicolon here is just notation I picked. has no semantics. And then the sequence, the relation really is over configurations. Sorry, keep mistyping that. So there's state here, so we have to define what that is as well. And in our simple case, we can again use a record here. We only have locals, so the state of locals is, well, their values. So this is just a sequence of values, essentially. That's our state, our local state. Okay, and now we kind of proceed in a similar fashion. Basically, for every instruction, we want to write one rule. So let's start with knob, which is sort of easy. So we have the state and the knob instruction, and that reduces to the same state because it doesn't have any side effect, and the empty instruction sequence, which means there's nothing left to be done to execute a knob. Right? For drop, we start similar. Yeah. So that also reduces to something empty, but it takes something from the stack, right? So which we can express as being there isn't a constant instruction before that. And that is what we have defined to be a value. So if you have a sequence of an instruction that is a value and a drop, then they can react and turn into the empty sequence, right? That's how you reduce. And when you do that iteratively, then you reduce your program. So I don't know if you can see that, if it's so low down. Select now is actually doing a little bit more work. So with select, we have two values and a third value, which is required to be an I32 constant. So we can kind of pattern match it directly here with some value, and you have a select after that. So what does that reduce to? Well, in one case, it reduces to val1, which is exactly the case if C is not 0. Okay? But we need a second rule for the other case. So there are now two rules here. So this would be true. Let's call this false. And then in this case, we reduce to, oh, sorry. Of course, this should be val2 here. And that's all you ever wanted to know about conditionals, right? You don't have to write a whole bunch of stuff. It's just these two rules that describe how a conditional works. And finally, we have locals. Local get. And this is where the stack comes, the state comes in. Oh, actually, I have to put the state here as well. Otherwise, it will complain. So we have local get x. And that goes to the same state and some value. Where does that come from? Well, we have to look it up. So if s locals x equals val, right? And the last one is set. This doesn't return anything. Instead, it expects something. So it's a val here. And it also changes the state now. So we get an S prime. So our side condition now is, what is S prime? And S prime is an update of S, and there's some notation, meta-level notation that SpecTag understands, which is, okay, I want to be that the same as S, except that .locals.x has been replaced with val. So that you can use this kind of path and replace that. So that's our entire reduction rules for this language, minus you need some contextual rules about like how you find the regex in the sequence, but again, I'm going to skip that here in the interest of time. And I effed up somewhere, 37. Oh, yeah, that should be this. Okay. So this is our specification. Well, we're not done there yet. We want to generate a document that nicely prints it, right? So that I prepared a little bit. So here's kind of like a template for this document we want to generate. So this is written for the Sphinx document processor. So you write a bunch of text here, and the interesting thing here is that for spec-tech we can put in these clauses, these splice clauses. And then we can run spec-tech over it. It will interpret these and insert the definitions to do so. So for that, I built a little make file so that I don't have to remember the exact invocation. Oh, okay, I renamed something. Sorry. I did it a bit differently before, obviously. Can never remember what I did last time. Right, so this succeeded now. And it produced an RST file with all the things spliced in. So this is now all the LaTeX it generated from these ASCII formulas. So it's nasty stuff you really don't want to write manually. It also generated prose for us, which is a bit harder to spot here. So let's actually generate a PDF from that to look at that. And PDF. Right, so this is now the document. Well, I had some template that does the whole thing around it, right? And there is a table of contents, blah, blah. So you have the abstract syntax, which is defined here. So this was text that was literally in the template. That was not generated. But if we go to, for example, all this text here is generated, right? So I just wrote the rule and the text is generated now. Maybe a more interesting case is the one for execution of select, for example, right? So now there are the two rules that you might recognize, but all this text now is generated automatically, and it knows that it has to somehow merge the rules and turn that into a conditional to produce this text. All of that is now nicely generated. How much is it left?
0 minutes.
0 minutes. Okay, then I'm just going to show the final slide here. This is how it looks on the real document. I'm going to skip that and just have the summary slide is why this is so useful, or what are what we get out of that is more efficient design and authoring, so that benefits proposal writers and spec editors. Higher assurance, as I mentioned before. And we also hope, as a third thing, like in the future, that other kind of tools can make use of having this machine-readable form of specification. And there are already some in the making, like Dongjun, for example, is working on a test generator, right? So this would be a smarter fuzzer that doesn't just randomly fuzz WebAssembly code, but actually understands its semantics, right? So it can take that into account. And you can imagine various other code tools that, or like verification tools that can now read in this definition and do something smart with it. Okay, I'm going to stop here. Thank you.
Thanks so much. So, let's take a short moment for questions. The way we'll do this is, Andreas, can you come to the side? Anyone who wants to ask questions, come up to the mic. Can we get our next speaker coming to set up their laptop as we do this?
So you talked about a whole bunch of things that you generate, but you didn't talk about what I think is the most important part of the specification, which is the reference interpreter.
Well, I briefly talked about one version of it. Actually, it's not really a generated interpreter, but it's a meta interpreter that runs on the specification you give it, right?
And does this sort of completely replace the reference interpreter now?
No, it does not. And that is something that is maybe some future prospect, but there are lots of things we have to work out before being able to do that. Right now, that can only interpret the execution rules. It can't do parsing, it can't do validation and all these things, right? I also didn't really talk about much about the whole mechanization side of things, but yeah, that's basically the second phase of our project. That is the ongoing work happening right now.
Yes, watch this space.
Exactly, yeah. Any other questions?
One more question. How do you think we're going to fund continued development?
Don't ask me. That's your job. No. Yeah, I think that's still the biggest question. Like, how do we sustain this kind of project long term, right? Because especially the mechanization, well, actually all of this is mostly done by academics, or and the nature of academics is that they tend to like to move on and they want to do publications, and like extended maintenance of software projects is not something they really get anything out of. So how do we do that? It's a bit of an unsolved problem. Right now we have a huge team and a lot of funding, relatively speaking, but is this going to stay that way? So that's definitely something we have to figure out still.
Thanks so much. Okay, thanks. I'll speak on that side. Now we have Rikito Taniguchi.
Oh, this is, oh, okay, sorry. Okay, so going to talking about using WASM-ZC and WASM component model in non-JS embedding. So my name is Rikito Taniguchi from Virtus Lab, which is a company working on Scala compiler and Science Tokyo. And this is a joint work with Sebastian Dueng from EPFL and my supervisor, Hidehiko Masuhara. And in this talk, I'm gonna cover the topics like compiler design and implementation using WASM-ZC and evaluation on compiler benchmarks and a little bit of micro benchmark on WASM component model function call with WASM-ZC. So let me start with a brief introduction to the compilation pipeline in Scala. The Scala is a high-level functional programming language whose primary compilation target is JVM, but it also compiles to native binary using LLVM, and it also compiles to JavaScript using something called Scala.js. And Scala.js is a Scala to JavaScript compiler, and we extended Scala.js compiler, and it is now generating WASM binary. And current Scala.js generates a WASM binary and a tiny little JS helper functions. So it works only in JS embedding, but we are also working on non-JS embedding like a WASM time using WASI and WASM component model. So let's get straight to the benchmark result. This is a benchmark comparison between JS and JVM and WASM. We compile the same Scala benchmark program to each platform, and we compared it. And this 1.0 is a JVM baseline, and each bar represents the relative execution time in JS and WASM. Blue one is JS, and orange is WASM. So to the left of this vertical line, the WASM is better, and to the right, to the left is WASM is better, and to the right, JS is still better. So as you can see, the WASM performance and compared to JS is pretty depends on the task, like computation-heavy benchmark and allocation-less benchmarks are faster in WASM, but still some of the benchmarks like doing a lot of JS interpretation or something JS is better. So in the rest of the talk, I'm gonna talk about the compiler internals and show you how some observation what WASM-ZC compilation slower. So let's dive into the compiler internals. So the first thing we need to do is to mapping the Scala object to WASM-ZC object. So in order to represent Scala object in WASM-ZC, we have to compile the Scala class into WASM-ZC struct type definition. For example, this point2d class is going to be compiled to struct type definition like this. It contains fields like x and y that corresponds to your Scala class fields, and it also has a virtual dispatch table that contains function references to the class defined in the class, and such as toString and hash code. And for example, when we want to call a method, we're going to get the function references from the virtual dispatch table, and then going to call the function reference using callref instruction. And interface method dispatch is kind of the same. We have one more indirection using interface dispatch table, but I'm not going to talk about details in this. So this is how we compile the Scala method call in WASM-ZC, but how about calling JS function? Because Scala.js allows Scala program to calling JS functions. Like for example, this makeArray2 function receives 2 primitive integers in Scala, and it constructs a JS array. And it's going to be compiled to WASM imports that takes i32 and one JS helper function that constructs a JS array. And Scala.js guarantees its primitive types, like primitive integers mapped to JS primitive on Scala.js interpolation. And actually, integer going to be compiled to i32, and i32 going to be JS number at the WASM.js boundary. So it works. It's OK. But it is going to be a little bit tricky when we work with generics, because now makeArray2 is a generic function that takes 2 generic parameter t, and it constructs a JS array of type t. And the generic parameter t going to be type erased, and it's going to be compiled to any ref, which is a top type in WASM-ZC. And so now makeArray2 and the import function is a function that takes any ref, but we still want to receive JS numbers in the JS helper function when with makeArray2 call with primitive integers. However, i32 is not a subtype of any ref, so we have to somehow convert i32 value to some reference typed value. But the problem is, how do we box primitives? Because remember, boxed integer should still be mapped to JS number. So boxing with a box class like a Java lang integer doesn't work, because WASM struct type value is opaque to JS, so it doesn't work. So what do we do is boxing i32 value or primitive values to JS numbers, JS primitives. Like for example, we are going to box i32 values to JS number, which is a reference typed value in WASM. And how do we box it? How do we convert i32 value to reference to JS number? Surprisingly, this weird identity function does the job thanks to the WASM.js interface specification. And this identity function is imported as a function that takes i32 values and returns a reference to JS number. And unboxed integer is opposite. So JS number is, of course, reference type, and the JS number is JS number in the WASM.js boundary, so it's all good. But calling a JS from WASM is pretty expensive, and it is high in profile. So in order to mitigate this performance problem, we use i31ref. i31ref is a 31-bit integer, target integer, which is a subtype of any ref. And fortunately, i31ref is converted to JS number in the WASM.js boundary. So yeah, boxing integer in i31ref is still fine. And it is efficient because there's no JS function call from WASM. So we use I31 ref for boxing 8-bit integer and 16-bit integer and 32-bit integer with runtime checking if it fits in 31-bit integer. And if it is not, it's going to fall back to JS number boxing. Yeah, that's good, but however, I31 ref is not applicable to all the primitive values like F64 and Boolean. So we have a new proposal that's called JS primitive built-ins proposal, which is JS primitive built-ins proposal is adding some efficiently callable new built-in functions that manipulating JS primitives. For example, we have it's similar to JS string built-ins. And for example, this proposal has some built-in functions that convert between I32 and JS number, and like F64 and JS number, and Boolean to JS number, and some testing functions. So with this proposal, we can box values quite efficiently. So this proposal is coming from derived from Scala.js use cases, but we are looking for some other programming language use cases. So please let us know if you are interested in this proposal. This is a proposal link. So far we've been talking about the JS embedding, but we are also compiling to non-JS embedding, so using WASI and WASM component model. So rest of the talk is about the WASM component model implementation in WASM ZC language. Oh, sorry. Oops. So for those who are not familiar with WASM component model is a shared nothing safe language agnostic interpolation mechanism. It defines a new linkable binary format called component, which includes core WASM modules. And instead of having a shared memory between components, WASM component model ABI defines we have to store the arguments and return values to linear memory, and VM gonna copy the linear memory to other components' linear memory. So that's how WASM component passing data between component to component. But current WASM component model ABI called canonical ABI requires all the arguments and return value stored in linear memory, but WASM ZC language such as Scala is in Scala, all the allocated values are allocated as a WASM ZC object. So, and WASM ZC object is not able to passing between components with current ABI. So in order to cross the component boundary in WASM ZC language, we have to copy from WASM ZC object to linear memory, and so that VM can copy between components, and VM copy it. And if the Scala use the received value from linear memory, it has to copy back from linear memory to WASM ZC object. So it is a quite huge overhead for component model function call. So I actually roughly measure the component model function call overhead. I define the identity function that takes a string and returns string in Scala and Rust, which uses a WASM ZC and non-WASM ZC language Rust. And we call from the same language, like Scala to Scala and Rust to Rust. And we use the same byte length string as an argument. And it turned out our Scala version is like 4 to 6 times slower compared to Rust. And yeah, I think it is because multiple copy overhead, because like for arguments, it's gonna be, we have to copy the ZC object to linear memory and VM copy it. And yeah, the return value also have to linear memory to WASM ZC object. So yeah, there's 2 or 4 copies in addition to the normal copy by VM. So yeah, that's quite slow. So how can we optimize the component model calling WASM-ZC? It's still an open question because just an idea. And I found a discussion on WASM-ZC object supporting canonical ABI, but I'm not sure it's going to be quite complicated WASM-BM implementation for WASM component model. Or maybe it might be nice to have a bulk copy operation between linear memory to WASM-ZC arrays, but I think it is only useful for string calls in component model, so I'm not sure it's a good idea. So I'm looking for ideas. So this is the final slide, conclusion. So we implemented Scala2 WASM compiler using WASM-ZC, and WASM is up to like over 3 times faster than JavaScript, but it is still slower in some cases, and one of the reasons is WASM2JS call for boxing and unboxing, and we have a JS primitive built-in for tackling the problem. And WASM-ZC language, we have a slower component model function call in WASM-ZC language, and we are looking for some ideas to speed up. So yeah, this is the end of my presentation. Thank you for listening.
Thank you. Could we please do the same maneuver again, where we swap these speakers and then have questions come up to the front? Is that okay?
Yeah, it's really cool to see that. Now we can't see the graph anymore.
Oh, yeah.
So it seems like the most inefficient benchmarks, they involve a lot of integer computation in the
Yes, that's right.
bit range, or is that the problem because of the boxing, I suppose? Right, okay, yeah. Another stupid question, is the WASM version still called Scala.js?
Sorry?
Is the WASM version still called Scala.js, like the JS-less WASM
No.
version?
Yeah, we are still calling Scala.js because WASM is said to be still experimental. So maybe in future. Yeah.
So with regards to your problem of having to do multiple copies in the component model setting, to me, extending the canonical ABI to handle the WASM-GC type seems like a total no-brainer. Mm-hmm. Have you kind of made this representation to the group, and how has the response been?
Sorry, could you repeat the question?
I think it's really obvious we should be extending the canonical ABI.
Mm-hmm.
Have you said that you want this to the component model people, and what has the response been like?
I haven't yet because I found the proposal like a few days ago.
Okay, you should definitely talk more because it sounds like a really
yeah,
good
sure.
idea.
This is something that's absolutely being worked on.
And it is definitely in progress, it like will happen.
Oh, that's good.
It's not entirely. There are many details.
I'm sure there are
Yeah.
things that can go wrong, but it seems like the right solution to this problem.
Yeah, no, I
Yeah.
agree, but the design space is huge.
Yeah. Thank you so much.
Thanks so much. Let's thank the speaker one more time.
Let me start with a disclaimer. So I'm presenting Michael's work. It's Michael's project, and I hope I'm in a good position to deliver it to you in the right way here. So in my group, we are, among others, interested in dynamic analysis of concurrency issues. Yeah, and now that in the near future, or actually right now, you can finally run concurrent programs also in WebAssembly, we thought it might be interesting to have tools to investigate these problems also on the WASM platform. So therefore, the approach that we are familiar with is offline dynamic analysis, which means we are kind of instrumenting the runtime environment with tracing, and then we collect execution traces, and then offline we are analyzing the execution traces to do prediction of databases, prediction of deadlocks. And one part is I would like to get your feedback if this is a tool that's interesting for you guys, if it's needed, what further developments are interesting here. Right. So I guess I can go pretty quickly over the first few things. Essentially, one difficulty that I'm saying we, but it should really be Michael all the time, that we encountered while setting this up was that WASM runs essentially in a well-specified embedder, but the embedder could be like anything. It could be a standalone WASM runtime, it could be a browser, and any services that are provided are really provided via these external objects. Now, like if the embedder has a chance, offers concurrency as a service, then it's via these external objects. Right. So then you got WebAssembly modules, and you all know the components of that. So you essentially have tables with references to functions and to external objects. Then when you instantiate the WebAssembly module, it obtains linear memory from the embedder. Globals are initialized, and finally you have the instructions that do their job. And well, I guess I don't really have to explain anything of that to you. So let me go over that fairly quickly. So the main thing that we learned when investigating it is essentially that you could have a single module, and then when it comes to concurrency, you can have several instances of this module running in the embedder. So that means here you have one instance, you could have a different module that is also instantiated, and then essentially usually they work separately. So here you have a separate memory instance, and everything is completely disjoint between the two. And one part of our journey was to discover how you can actually create a shared space where two things can actually communicate in shared memory, like when you're translating a Rust program or even a C++ program into WASM. Right, so what we need for multi-threading, which is provided by some of the embedders, is we need some sort of atomic memory operation instructions, we need wait notify, mutex implementations, and we need to somehow obtain this shared linear memory, which isn't usually provided. Right, so this is the situation that we had before. So now this is what we would like somehow to obtain. And unfortunately, you have to jump to a couple of hoops in order to achieve that. Right. What we did in order to achieve that, actually that was like the second iteration, we thought, okay, so first we're going to insert an abstraction boundary so that we can abstract over the differences of the embedders. Yeah, so the first step here kind of provides what did he call it? Oh, he has a name for it. An ABI through which our object programs, well, the WebAssembly modules can uniformly access the concurrency services from the underlying embedder. Yeah, and this is kind of specific for every embedder, but on top of that, later on we're going to talk about tracing, and that's going to be oblivious of the particular embedder that is below. Now, therefore, trace generation runs on top of that, because otherwise, I mean, before the first version, we had essentially two different modules for this trace generation, one for a standalone runtime and one for the embedded JavaScript runtime. And that felt like a bit wasteful, and also we felt that this lower level would be an interesting contribution, interesting module by itself. Right, yeah, so that's what it looks like. So this is kind of the bottom layer of the previous diagram. This is the internal runtime ABI, and then on top, and then this would run on top the native embedder or the JavaScript embedder, and you have to set them up in quite different ways. And the execution tracing would live somewhere inside here. So what does this ABI look like? It essentially consists of some imports and exports. essentially the the imports are kind of what your module you want to run, the threading primitives that it can use, and then the other ones here you have to notify our framework about thread starting and obtaining memory and freeing memory. So that's what this ABI roughly looks like. When it comes to tracing, then we actually need some more, but we'll come to that in a few minutes. So I think 5 minutes or how much?
You have over 10 minutes left.
Over 10 minutes. Okay, so that should be plenty. So now we can get to this issue of getting to shared memory. Right. So if I have a module, then you instantiate it, and usually you get this memory instance. You can do another instance, and this is usually not the way that it's set up. Yeah? So we would like it to, if we want to have these two threads communicate, we would really like them to refer to a single memory instance. But if you straightforwardly instantiate it, it's not happening this way. So, but nevertheless, for each thread, you have to create a new instance of the WebAssembly module in order to get started. So, so depending on which way we want to run it, so with our infrastructure, you can either run it straightforwardly. You first have a patch phase, which I will get to in the next slide, which kind of explains how you squeeze the different instances into the same memory, and then execution. And in the other case, you also, when we want to trace, we also have this patch phase. This is then followed by instrumentation, execution, and during execution you generate traces, and then you get a trace essentially in a standard format that's used by various tools, written by us and also written by other people in the field. Right. Now, so if we were naively creating different instances that all point to the same linear memory, then we're in trouble, because the standard instantiation maps static data somewhere. Maybe that's okay, but then it also has allocates a stack area, and if we are naive, then all the stack pointers of our 3 instantiations of the module, they all point to the same area. Okay, this is not a good idea. So there are tools around, namely WASM-BindGen, which does some patching, and it essentially creates a layout like this. Yeah. So the sorry. So only the first instance gets the normal space for the stack. The static data is shared among everybody, and then for the remaining instances, the stack is actually allocated in the heap. Then there's thread local storage, which is also allocated in the heap. What is currently unclear to us is how you make sure that this allocated stack space is actually enough. I mean, you would probably have to have some analysis if you can do that. We didn't do that, and we didn't find that specified somewhere. Now, so basically for for our ABI, we mimic pretty much what WASM-BindGen was doing and extended it so that it worked with our stuff as well. All right, so we're getting pretty much to the end. So if you actually want to do this tracing, our tracing tool, we looked around on the market, and the only one that was working at that time was Wasabi. So for tracing, we extend the ABI that we don't just get, that we don't just get the usual threading messages, but that we also get messages when there are read and write operations to the shared memory. Right. That's actually pretty much it. From that, you can generate records that contain all the information that is required for this rapid bin format, which is then the input to our tools. And unfortunately, since I'm not Michael, I'm not really able to show you a demo of that, so you would probably have done that. So that's all I have to say. Thank you very much.
Thanks so much. So you've single-handedly put us back on schedule, so we don't do the rush thing. If anyone would like to ask some questions with the slides, please come up to the microphone. Can we get that microphone activated?
Hi, I'm Burak from working for Google these days. And did you find any bugs?
Not yet, not yet. So we right now, we just got the stuff more or less to work, and there are a couple of smallish examples that we were running. And now in the next phase, so Michael is working on his master's thesis. So and the idea for the master's thesis is to actually find a nice corpus of concurrent Rust programs and see what the tool does with those. And so if any of you has suggestions for what programs would be useful, because this is actually a real pain factor, because you need to find programs that use concurrency somehow in a meaningful way, that are not too big. Then you need to configure the inputs. So it's a lot of work to build such a benchmark suite. Yeah, and it seems that Michael is actually interested in doing that. And so any input there would be really very welcome.
Excellent, thanks.
So for that, I suggest talking to Arjun. He's done a little bit of work on race detection for WebAssembly.
Right.
So about this binary format, this rapid bin, what kind of tools do you have that consume this, and do they work like in a streaming fashion? Are they offline tools?
So they're essentially offline tools. So the rapid bin format is a compressed binary format for these traces, and that's conceived by there's a famous group. Here, these guys here, Umang Mathur. Maybe he's even here. So he's in Singapore. So he has built huge tool sets that work on this format, and many other tools, well, from researchers in that area also work on that.
Cool.
So that's why we chose it.
Cool.
So Chris Woods from Siemens, and I can't give you Rust examples just yet, but I can give you a huge body of C-based concurrent examples, and we're bringing them to WebAssembly, and your stack observation and knowing when you're bringing code over what the stack size should be is a big problem, and we go into it, and I am happy to give you a whole bucket load of examples. Please come see me afterwards.
Yes, excellent, thank you. Great.
I'm sorry to ask a technical question, but for the off-the-web side of threads, are you using the WASI threads interface or something else?
I should defer that to Michael. I'm sorry. So he did all the technical stuff.
Then that's perfect. Thanks so much. Let's thank the speaker one more time.
Thank you.
Let's change it. You have one more question. We do actually have time. Please ask it, and John, please come up.
Thank you for the talk. I have a question about the algorithm that you use. About the algorithm for checking the data race reduction.
Yeah.
Were there any challenges, or could you just use it out of the box, or did you have any changes to the algorithm that you needed to?
So okay, yeah. So since we are using the standard format, we can use tools that are available. We also developed some of our own tools, but I mean, so Mathur and friends have lots of tools that are well tested and well published. So
okay, thank you.
All right.
So I guess my talk sort of starts off where Andreas's talk ends. So he told us about all these amazing things about that WebAssembly has. And so this talk is going to be sort of maybe a little bit, like a spoiled child saying, well, okay, but we want more. And it's a bit of an ad for a research program around WebAssembly in Aarhus. So maybe the starting point is, why is WebAssembly successful? And WebAssembly is successful for a whole bunch of reasons. It's portable, it's got high performance implementations, it has a cool logo, many other things. But one aspect that I'm going to talk about that I find is particularly important is safety, which is, I don't remember who it was, maybe Conrad you remember, but it was I think a WebAssembly workshop where someone described it as a sprinkling of fairy dust that adopters would sort of be lured by and go to WebAssembly and start using it. And this idea is that safety sort of makes adopters and users sort of feel comfortable about the language. But what does it concretely buy them? And so the question is, what is safety, and in particular, what is safety in the context of WebAssembly? Maybe the first thing to answer is, what isn't safety? Safety is not a single thing. It's not clear to me what a master definition would be, even if there is one at all. And so it's an open-ended process. We have to find out what it means. I think it also depends on the language. Different languages will have different definitions of safety, so it's not like we can take another one for WebAssembly. And even within WebAssembly, I think different users have sort of different concerns or different threat models. So in particular, Chrome assumes that type checking goes wrong because it's too complicated. And as Andreas described, WebAssembly changes over time anyway, and so this changes what the definition of safety is, and I can give you a concrete example later. So why should we even care about safety? Well, there's this famous paper, Everything Old is New Again, where they show that, in a sense, safety is easy to misunderstand, and people have misunderstood it in the context of WebAssembly, and sort of this has had consequences where people thought that the language gave them something that it didn't give them. And so my goal, my interest is to clarify and state what this sort of fuzzy fairy dust is, and try to show maybe that it's real, that you do get some concrete guarantees. So what is safety, or maybe what are aspects of safety? So one that Andreas described, and one that is actually in the standard, right, is type safety. And this is, as Andreas said, it's a very old notion, and Conrad gave us sort of the version of that, or formalized the version of that we have for WebAssembly. And so this gives us like a very concrete aspect of safety. But it's only one aspect. I think there's other aspects. One of them that I think, if I remember correctly, the standard kind of hints at is some form of control flow integrity, that there's some separation between code and data. And of course, everyone sort of informally knows that about WebAssembly. You look at the language definition, and you kind of see, okay, the two are separate. But it's a very sort of fundamental thing when you're thinking, okay, I want to adopt WebAssembly as a technology. This can really be a sort of an important property that makes you think, okay, this is a good fit for what I want. This is really an important guarantee for me. But even within sort of control flow integrity, there's different aspects. There's this pure sort of Harvard architecture, code and data are separate, but there's also the aspect of well-bracketed control flow. So if you have calls to functions, then they behave in a well-bracketed way. If you call f, then G should return before f can return, right? You don't have f, G, F, G. That's not a sequence of things you can observe. But this changes with stack switching, right? This completely becomes possible, this kind of sort of subversion of control flow. So it's a thing that has, it's a part of safety that has changed throughout the still relatively short history of WebAssembly. And you might imagine that people who sort of designed their threat model, designed their sort of idea of why WebAssembly is the right thing for them, they might be surprised if suddenly there's a new language feature that kind of breaks this. And then there's lots of other aspects of safety. So for example, everything to do with side channels and all the side channel based attacks. I think WebAssembly sort of doesn't promise much in that direction, although there is this work by Conrad and others on sort of constant time versions of WebAssembly that do guarantee you a bit more. And what I'll focus on sort of mostly as an example here is isolation. All right, so here the idea is sort of isolation of parts of your programs between each other, and there's many aspects to that, and I'll return to that. But the idea is, as I've kind of sketched, that between all of these different aspects of safety, some of them, like the first one, are very clearly and explicitly stated in an appendix to the standard, and some other are sort of much more fuzzy. Fuzzy both in what they mean and in sort of how precisely they're stated and described, and how authoritatively they're described. So to zoom in on isolation, well, isolation itself has several aspects. And one of them is sort of what I'll call external isolation, which is sort of the umbrella of sandboxing, right? So it's an isolation between the program and the outside. And if we zoom in more specifically, something like, well, the program doesn't access memory outside of its linear memory, or doesn't try to access things outside of its linear memory. And this is at the same time a property of the language. You know, WebAssembly sort of has checks at every step of the execution, but it's also a little bit a property of the runtime. You know, you could perfectly imagine having an implementation of C that does exactly the same thing. It's not what the language requires, but you can do it. And there's another aspect of what I'll call external isolation, which is that the process doesn't manage to access memory outside of its process, rather than it doesn't try. And this is, well, it's not so clear. Is it a property of language, or is it a property of, you know, the operating system and its process isolation? So in a sense, it's not really, you know, in the context of WebAssembly, whether the program is sandboxed is not even clear that it is a property of WebAssembly, even though, you know, people associate very much WebAssembly with sandboxing. So I think it's worth bearing these things in mind. Andres is making very funny faces. I don't know if that's success or failure.
Yeah, because I mean, the semantics tells you what is happening with every possible execution, and none of that involves any sort of dependence on outside state, right? So how
well, yes, but it assumes that your runtime is implemented correctly, and in a sense,
well, sure, but I mean, if your implementation isn't correct, then none of the guarantees of the language will anyway.
You could also have a correct runtime that just arbitrarily mutates the external state on every step of WebAssembly. You preserve the WebAssembly semantics.
Whenever you do an add, it just writes to a random location in memory outside of your WebAssembly program. It's a bit contrived, I agree.
But that would not be observable from within WebAssembly, right?
Yes, but I think...
Well, except through host calls.
Yeah. Okay.
Except through host calls.
But then it's sort of a semantics of the host call.
Yes.
Yes.
That's the point.
Yeah.
Which I think... My point is, you really have to think about these things. It's really like, sort of, it's easy to sort of think in a very naive way and zoom in, oh, you know, there are these checks and therefore it's all fine, but you actually need to think about, you know, maybe there's this sort of weird, not quite side channel, but a secondary channel that sort of loops back through host calls. But I move away from external isolation and zoom in on internal isolation. And this is really isolation between parts of the program. So sometimes people call that local state encapsulation, or there's a bunch of other terms. And the idea informally is that things that should be separate actually stay separate. So for example, this is things like locals can't be accessed outside of their function, which is very different from, let's say, languages like C. Right? So this might be, again, not a very strong reason to adopt WebAssembly, but it might sort of encourage you a little bit. Like, it has this kind of sensible structure. Another property that's maybe more important for sort of actual use cases of WebAssembly is that one module's non-exported memory can't be accessed from other modules. Right? And these are really purely properties of the language, right? This is a thing that, when you're reasoning completely about your program, not the interaction with the outside and other things, it's really, you're defending part of your code against other parts of your code. And then there's many other types of isolation, but I want to zoom in on this one here. And the reason is that this is really to do with language properties, all right? So language properties, I think, are important because users implicitly, also a little bit explicitly, rely on them when they program. And also because they're a very important use case of WebAssembly. As I said, I guess, sort of underlying many of the use cases of WebAssembly, let's say in edge computing or things like that, there's this idea that if you link with another module, or in WebAssembly terms, if you combine with another module, like if you instantiate two modules next to each other, then it's going to be safe. Like there's nothing that the other module can do that isn't explicitly allowed by a very well-defined and clearly delimited interface. So in a sense, if you link, or if you instantiate together with a sort of evil module, the worst thing it can do is trap. It's not going to corrupt your own internal things. And in a sense, WebAssembly makes this sort of possible and easier. And with the context of WebAssembly, you can really define what it means to be safe. And so there's this term, the universal contract, that has been introduced by the people cited at the bottom in the context of instruction set architectures. But the idea is that it captures a property that's respected by sort of arbitrary code in your language. Right? In WebAssembly, importantly, is any well-typed code, because instantiation will sort of kill any code that is not well-typed. Right? And so this universal contract, it gives you a guarantee about no matter what the rest of your program does, I know that my part of the program will always have these things that it continues doing well. So for example, if it has a non-exported memory, then it remains the only one with access to it. Right? And it's related to things that people like Wadler have called three theorems. It's the same idea in a sense. And so here is the point where I'm going to say, well, all the things that Andres described or offered us, they're nice, but I think we should have more. I think that the language standard, in a sense, should declare upfront some of the language guarantees of these universal contracts so that users and adopters know what they're buying. I mean, there's already, we're already on the way, right? I don't think there are that many languages that include a stated type soundness in the standard itself. But I think we can, and I think we should do more. So really the plan, and this is not just a plan for me, but I think it should be a plan for the community, is to identify these properties, state them, formalize them, and this is where it becomes maybe a bit hairy, prove them, and then make them part of the standard. And I think the idea then is that if you have a proposal that you want to extend the WebAssembly standard, then you should show not only not make implementations, but not just define new rules, but show that when you added these new rules, you don't break old properties that people expect of the language, or if you break them, explain, so give a good reason why you break them, and maybe give a fixed version. And I guess the stack switching example, it's a case where sort of along the history of the language, you have this, like the naive version of the property was broken. And this might, I'm not saying it actually happened to people, but it sort of gives a flavor of the kind of ways you might be sort of backstabbed by an evolution of the language if you don't have these very upfront stated properties. So in a sense, what I want to do is sort of a call for help, because I think there's lots of these language properties, and lots of people, different people have different requirements, different expectations about what safety is. And me sitting in my office, I can't really figure out all of them, let alone figure out which ones are important. I think we should have sort of as a community a discussion about these things to identify what are the universal contracts that people actually rely on in practice. And this is really, this is the main statement of my talk. And then the rest, I'll quickly describe a sort of case study of how we've tried to do that for one specific flavor of safety and why it becomes a little bit complicated. And so why maybe this very lofty aim, there's already speed bumps on the way. So zooming in on local state encapsulation, there is this expectation of sort of coarse-grained encapsulation, a coarse-grained isolation at the level of the modules in WebAssembly. Right? So if you state it in a sort of very rough way, one module's non-exported memory can't be accessed from other modules. That's, informally, it's a pretty good thing. I don't know whether the standard actually states that. In a sense, I think in the standard it's an emergent property. It's sort of like an accidental property of instantiation that it actually guarantees that. Well, it's not. I mean, it's not accidental in the sense that clearly it was written by humans with a purpose. But if you look at the document, it's an emergent property of the individual rules.
We actually discussed it, right? I would love to have some formulation of this statement, but like, how do you formalize that exactly? Like, I haven't seen any good solution to that.
Like this.
Involve 23 symbols. Okay?
I think 20, as you will see on the next slide, is a bit of an understatement. So I think, but I still think it's, even if the end might not be the most pleasant thing, I think the journey is still important and some of the milestones are important. So you can try to refine it by saying, well, one module's non-exported memory can only be accessed sort of through that module. So other modules can access it if they find a function from the module that sort of allows them to mutate that memory, and then it's only according to that function, in a sense, right? So, and then if you try to make that more precise, then it turns out to be a little bit more thorny, which is, I guess, the whole thing with contracts and ferries ending poorly. So if you try to make that precise, or at least to make a version of that precise, it kind of looks like that on the right here. So this is, I think, excerpted from Einer's thesis. And really, I'm not expecting you to read the tiny Greek letters. The point is more that basically reentrancy kind of makes that complicated because, as I've kind of already sketched, one function from your module which has access to the private memory might call some unknown function, which might be written with sort of ill intent in mind, which might call back into you, and it might call back in a sort of very twisted way. And so the interface of exactly how much it can do to your memory despite your best efforts when you're defensively programming it is a bit thorny. But while this is kind of horrible, I mean, it's a definition. You can prove things with it. You can prove it in a theorem prover. But it remains, I think, the domain of experts in a sense. I don't think a new adopter will sort of look at this and go, oh yes, this is exactly what I meant, right? But I think what we can do instead is sort of look at concrete programs and sort of see what this big definition gives us on these concrete programs. So here it's written in sort of terrible Java-like syntax that if you have a memory that you don't export and a function that has access to this memory, and where it's sort of an increment by 2 function, right? And so if it starts from 0, the memory is initialized to 0. If it increments by 2, then it should always contain, in the part of linear memory that it increments, an even value. Except that in the middle, because it increments by 2 in 2 steps of 1, you sort of temporarily break that. Now, of course, this is a silly example, but you should imagine in a bigger program that you have your module that has access to some sort of precious resource, and it can internally do potentially dangerous things, but from the outside, this should never be achievable, right? So that no evil, malicious module that you instantiate with can sort of lead you into a bad state. And then we have this function g, which is also from this module with access to this precious private memory, that calls into this unknown function that might itself call f. And so g calls h, which indirectly has access to the memory through f. And what we need is some way to state and to show that f is safe to call, even with arbitrary code in h. And this is sort of the umbrella term for this is robust safety, this term from the model checking community, this idea that you're not just safe on your own, you're safe when you're combined with potentially malicious environment or rest of the program.
Is that the same that some other communities call representation independence? Or?
I think it's linked. It's not necessarily exactly the same. I think robust safety has this idea that you also have a sort of functional spec. It's not just about the sort of representation. but it's very much linked. I don't think there's a clear boundary in between the two. And sort of a high-level sketch, the idea is if the 0th entry is of the linear memory is the one that contains the integer that we increment by 2, then before and after each function call to that module, this is even, but maybe not during, right? F breaks it temporarily. And then G, when we want to make sure that G is robustly safe, what we need to do is make sure that whatever the call to H, this evil function, does, is not going to change this memory here. And to do that, what we can do is leverage this idea of ownership as used in separation logic, and to say, well, when reasoning about the call to H, the evil function in G, we have to, like the logic forces us, to give H ownership of everything that it has access to or it could get access to sort of transitively. And then with a suitably defined logic, as I flashed a few slides ago, then we can show that this does not include the private memory, and so we know that, in a sense, it is safe. And Maxime's talk later will talk about that in more detail. And so to conclude, safety has many aspects, and some of them are clearer than others, and I think we would benefit from clarifying what these are, although it won't, as I've sketched, always be so straightforward to do so, and really sort of bake them into the standard so that, as universal contracts, so that users and adopters know what they get from the language, rather than as an emergent property, but really as an upfront guarantee. And I think for all of this research, there's really sort of a deep link between what people care about when they use the language, which is a bit obscure to me as an academic, and also this relatively complicated verification-linked techniques. And I think we need to talk, both me and all of you that know these things, and as a community about how we can improve WebAssembly like that. That's it.
Thanks so much. A few questions and then lunch.
Woo. Yeah, I mean, I agree with almost everything you said, obviously. I have two comments. One is with respect to what you called external isolation. So the spec actually has in one of these appendices the embedder interface, right? Which I guess we could take a bit more seriously, maybe even formalize in some way, and then it would specify some of the things you can do and can't do. So it would rule out the weird example you mentioned before, right? Because that's not something you can do through that interface. That would be one thing. The other thing is more like a question. So you said that stack switching violates well-bracketed call returns. I don't quite see why that would be the case. I mean, it's still structured, right?
Well,
you can't return from a function that you call transitively. You still have to return from the outer function last. I don't think stack switching can change that.
Well, yes, but sort of the naive property that you really have this stack of F, G, G, F.
Yeah.
This kind of breaks because you can sort of jump up and down through things. Like the sort of the obvious notion. Like, I mean, clearly there's a property that WebAssembly 1 has that WebAssembly with stack switching doesn't have anymore. And sort of the extremely naive control flow doesn't happen, is not guaranteed anymore.
Yeah, I guess it depends on how you model it, right? Because we have different stacks, so like you can only...
Yeah, but already you're saying, but if we have different stacks, right? And suddenly you need to change your model, your mental model.
If you view these as coroutines, then you can't have, then they are not nested calls anymore, really.
Yes, but then that's exactly my point, right? You need a more complicated mental model.
Sure, but I would still maintain that exact property, at least as stated, is still preserved.
But I guess it depends how you state it.
The very bare minimum you'd need to do is have some concept of a suspension is analogous to returning from a call with respect to the bracketing, right?
Right, which it is not, right?
You see, this is why we need to clarify these things.
I'm surprised you're not just agreeing with me and saying yes.
No, I mean, that's suspending, you're not returning.
Yeah,
you
but if
still like, once you return, you still have to do that with the inner function that still has to return before the outer function. There's still no way around that. You can suspend, but you cannot return before the outer function, after the outer.
Yes, but you can return from the other function without having returned. You can return from the outer function without having returned from the inner function in a way that is maybe surprising if you have a very simple mental model.
Not in the way I would define inner function. You can only do that in if the inner function is in a coroutine, but not if it's in the same. Right? Okay, maybe this is too far.
Oh, your point is you're viewing the handler as like a barrier, and that's the point at which you start caring about well-bracketed calls.
It's a separate computation. You're suspending one and working on another, and your inner call is a completely
Then the bare minimum is you have to start modeling handlers this way.
Yeah, sure.
Yeah, okay.
Anyway, sorry.
No, I think this is an excellent point of why we need to clarify these things, because even experts have like different mental models and don't necessarily speak the same language.
Okay, one last question, then we'll break for lunch. Go ahead.
Yeah, I just wanted to, Burak again from Google. So in the context of memory safety discussions, like I cringed also a little bit when I saw the like safety can mean so many things, because I often like talk to the security guys who, by the way, mention all these things and they're super valuable and one should sort of be enabled to talk formally about them. But then I go and I dig out this very old thing that these ML standard, which I also like admire, you know, and also like, you know, the very basic property that in academia languages have and that outside languages don't have is the absence of undefined behavior, the absence of untrapped errors, right? You don't want the program to continue execution without knowing what happens. And we don't live in this world. Right, like in academia, we understand the value of that, but despite decades, right, like people are still using C and C++. So there's at least one sort of handbook article by Luca Cardelli that defines safety. It's a technical definition, right? It says safety equals absence of untrapped errors. Now I agree it's a technical definition. So you can, of course, take other definitions, and maybe not the most universal, but that's definitely the definition that I can find in the WASM spec, and that, you know, and that's a valuable thing. That doesn't mean that the other things are not also valuable, especially the thing that Andreas called representation independence. I've seen in the semantic type soundness paper that has been called data abstraction, which what does it have to do with data abstraction? Well, it means what they really mean is isolated stuff stays isolated, and they also use iris to formalize it. So that would be very valuable. But you know, can we find a way to advocate for this without you know, giving up on that notion, that very simple notion of sort of language safety, meaning absence of untrapped errors? Because absence of untrapped errors does remain. It's not, like outside of academia, it's not the standard yet. And people don't understand it either, because the C++ spec means undefined behavior means my compiler can optimize, right? So that, like, is there a better way to talk about these things without, you know, that would be my question.
So I think that the sort of absence of untrapped errors is just one tiny corner. It's very good that WebAssembly has it. I don't know whether it's stated ever.
Well,
I guess it's a consequence of type soundness.
Probably of type soundness. There's no undefined behavior, right? Otherwise it would be type soundness.
But this doesn't include things like, for example, if you have the example I gave of if you have a module and you don't export it, then other people can't touch it.
Yes,
right? This is completely fine. You know, it doesn't lead to untrapped error.
It's what some people call memory safety, right? So maybe we need to be better about our qualifiers on the word safety.
No,
yeah.
So, like, there's a distinction between syntactic type soundness and semantic type soundness, right? And this is like what some call semantic type soundness. That is beyond just the syntactic. Okay, you don't have undefined behavior. You also have certain semantic guarantees beyond that. But yeah.
Maybe that's the way out, because I mean the same security folks that talk about memory safety, they never come up with super clean, crisp formal definitions. There's like, there is no use after free, etc. Right? So if you're looking for precise things, then maybe semantic type soundness is the way to.
And I would argue that WebAssembly is memory safe with respect to its own memory. Right? That doesn't mean that anything you compile into that has its own more fine-grained memory model is memory safe with respect to that model. But that is a different layer, and that's also actually often leading to confusion.
Yeah, that was what the Everything Old is New Again paper was talking about, largely.
And essentially also what Line is formalizing, right?
Yeah. Well,
But isolation definitely very valuable.
Let's continue this discussion offline. Thanks, we go on last time. Well, everyone, we now have a lunch break. Please come back for 1:45. If you are the speaker who wanted a table for the
How are we looking? Good?
All right, everyone, thank you for coming back. We've got great attendance. Welcome to the second session of the WebAssembly workshop. I'm very happy to announce our second keynote speaker, Oscar Spencer, who's going to be talking about WASM-GC and the future of high-level language compilation. Please take it away, Oscar.
Absolutely. So thank you, everyone. My name is Oscar Spencer. I'm a co-author of the Grand Programming Language. I also am on the technical steering committee for the Bytecode Alliance, but that's not really relevant for this talk. And yeah, I'm going to talk about WASM-GC. So first, let's talk a little bit about garbage collection. So low-level languages like C require users to manually free allocated memory. So you as the user of the garbage collector. High-level languages add code to your program that automatically free objects when they're no longer used, and that's the garbage collector. Garbage collectors are often very large and complicated, which can affect WebAssembly modules adversely. So if you're a low-level language like C, this isn't really a big deal. Your WASM module, only a very small % of that module is code for, say, malloc and free, right? Very little code that affects your WASM module. But if you're a high-level garbage collected language, this isn't ideal because you've got a whole garbage collector that you're shipping with every single WebAssembly module. And that's not fun. We want to have our WebAssembly modules be nice and small, right? So before WebAssembly GC, the way that garbage collection has worked has been that the runtime hands you a chunk of linear memory and says, hey, have at it, do whatever you want. So if you want to throw a garbage collector in there, go for it. If you're going to do something else, that's completely up to you. But browser engines already have world-class high-performance GCs. So there's generally no reason for compiler toolchains to have to include a full garbage collector into every single WebAssembly module. Granted, if you want your garbage collector to do something ultra fancy that isn't supported by the runtimes, that's a different story. But for the most part, you can get away with just using the garbage collector implementation that's already in the place where your WebAssembly module is going to run. So goals of the WASM-GC proposal, provide a way for WASM modules to utilize a runtime's garbage collection implementation and make sure it's generic enough to work for any language. So this is the dream. We have a WebAssembly module where there's no memory management code whatsoever. All of the code in your WebAssembly module is just your user code. That's the absolute dream. So what does this actually mean in practice? Well, you can make structs and arrays. That's what the GC proposal is. So a lot of folks get really worried when they hear about the GC proposal. It's like, oh, WebAssembly has this whole GC thing that I have to worry about now. All it is you can make structs and arrays, and then ideally, maybe, possibly, they'll be freed at some point. That's the idea. It's really simple. If you look at this WebAssembly code here, we create a new struct. It's got some values in it. We create an array. That's it. It's really not too scary. That's everything that has to do with WASM-GC. So the important thing to note here is that the proposal does not prescribe how garbage collection happens. So the runtime itself, or the runtime that you choose to use, can decide what method of GC is going to happen. So let's say you've got really short-lived executions. Maybe you have something that's just a function that's going to execute one time, and that's it. Do we really need to do GC? Probably not. In fact, my favorite GC implementation is exit. It works really, really well. I highly recommend if you've never tried it. But if you've got a real-time application, something that's really intense, it needs to run continuously, maybe you want to have something like a reference counting algorithm, where it's like you amortize all the garbage collecting over the course of your program, so you make sure that, okay, this is always going to run very consistently. Versus if you want something to be really high performance and you don't mind pauses, you can have a massive mark and sweep GC, that's fine. But this is completely up to the runtime that you run in, right? This is not you doing something to your WebAssembly module to change how that works. And so that's a big deal. Your WebAssembly modules and any compiled dependencies that are in there don't need to change for the type of environment that your code is going to run in. And so that's a big deal for portability with WebAssembly, right? So we get a bunch of new reference types. So we have func refs, so you can explicitly reference a function, extern refs for values that are outside of the WebAssembly VM. And then we've got this nice, beautiful type hierarchy of any refs. Underneath those EQ refs, those are references that you can check if the two references are the same. I31s, which those are for your unboxed scalars. You lose a bit, so the runtime can use that to say, okay, this is a value that's on the stack and not a pointer. Structs and arrays, which we mentioned before. You get field types. So your field types for your structs and arrays can be any of the core number types, I3264s, F3264s, or any reference type. Fields can have a special pack type, so they can be packed I8s or I16s, and fields, of course, can also be mutable. We also get a wonderful subtyping system where you can declare your struct and array types as open, and that allows them to be subtyped later. So this is a big deal. One thing that I'll note here is that the way the subtyping system works, if you have an array is a subtype of another array. If its field type is a subtype of the other field, and for structs, it's the first in fields of that. This actually is really elegant, in my opinion, for how this works, but we'll talk about that a little bit more later. We get a bunch of new struct instructions. So struct new and new default, so you can create a struct with values, or you can create one with just default values. Get, signed, and unsigned, set, same deal for arrays. But we also get these beautiful new data, new elem. So if you have data segments or element segments, you can initialize from those. Additionally, arrays keep track of their lengths for you. So if you're a compiler author and you are used to storing your array length somewhere, you don't have to do that anymore. You can just ask the runtime for it, which I like that, makes me happy. For those unboxed scalars, you have ref I31 to create those I31 values, and then you can get the value back either sign extending or not. Casting. This is where things get a little bit more fun. So ref test, you can test whether reference is of a certain type. The cast instruction, you can cast both up and down, so you can lose specificity or you can gain specificity. You will incur some runtime costs for doing that, but maybe that's okay. And then you can do branch on cast and cast fail for if you're trying to get real dynamic and have a bunch of fun there. And of course, we have that ref EQ instruction to test equality for references that are EQ types. I want to talk about some of the quirks of WASM-GC. So non-nullable locals. If you're writing a compiler, this is something that you might run into, that I ran into, that I thought was kind of annoying. But locals are only evaluated in their current block context. So what this means is, if you look at this function on line 3, we have this local that's a struct, and that struct, it's not a mutable local, right? We're just going to keep the value in there. In this block, we initialize that local with this struct value. And then outside that block, we try and get the value of that struct. And this is a validation error. Why is this a validation error? Because it would be horribly complicated for the validator to test whether or not all your locals are actually initialized everywhere. So this is a restriction. That is okay. I'm fine with this restriction. But depending on the way your compiler is set up, you might have to do some refactoring to deal with this. But that's okay. The next is mutability. So it's possible to create immutable recursive types, but it's impossible to create values of those types. That's partially because immutable types are not subtypes of mutable types. I brought this up, and Andreas was like, just because your language has these immutable structures doesn't mean the implementation has to be immutable. But Andreas, I say this, I want it. And but there are actual real reasons why you might want something like this. The first thing I think about is optimizations. It's very easy for your optimizer to see, oh, this object, it's immutable, it doesn't get used, it's never getting mutated, we can throw it away and do optimizations like that. But if you think about things like the component model, which we'll also talk a little bit about, I might want to pass a reference to a struct or an array from one component to another. And in the component model, I can do this without a copy because it is semantically correct all the time if it's immutable, and maybe some of the time if it's mutable if you're able to prove a couple things about it. But this is actually a big deal. So this is something that's being discussed, something that might actually happen. And the last quirk that I'm going to mention here is arrays of mute I8s. So if you're not using linear memory at all anymore and you want to have an array of just data, of just bytes, we don't have efficient ways to load or store 16, 32, or 64-bit values with this. If you want to deal with a bunch of 64-bit values, you could just use a 64-bit type. But if it's just bytes and you want to get one value out, then it's annoying in the other way. This is not something that I'm worried about. Everyone who sees this says, yeah, we can add that. That's fine. So that also makes me happy. Let's talk about Grain. Grain today, it's linear 32-bit memory. GC is performed via reference counting, and we only leak memory sometimes. Yeah. That's the dream, right? But some of the major considerations here is Grain has fully generic first-class functions. So we want to do things like list.map, and we want to compile that thing one time. We don't do monomorphization or anything like that. We want a truly generic map function. So to do that, we have to have a uniform data representation. This is what compiling an apply function, so a function that takes a function f and a value x and applies f to x. This is what this compiles in the linear memory version. So if you look on line 2, we have 3 parameters. We have 3 I32s. The first one, that's closure argument. Don't worry about that. The second 2, they're I32s, which, yes, I said any value, but we have to have a uniform data representation to represent this properly in Grain. We chose I32s for that. Decref, that's a part of our reference counting, but we do a call indirect. So we pull the pointer to the function in the function table from the closure, and we do a call indirect on it. That's how that gets compiled right now. So we got to do something. We can't use I32s anymore. That's not going to work. So what are we going to do instead? We're going to use any refs for everything. So that's fine. It can be anything. Well, what's wrong with that? Which, that's a little bit sad if you think about it, because WASM-GC gives us all these rich types for heap values. But if we actually use those types in the type signatures, then we'll get the same issues as if we try to use values other than I32. But that's OK. With some fun compiler optimizations, there's lots of times where we can just use those values and avoid a bunch of casting and things like that. But on that note, ref casting everywhere sucks. It's awful. I hate it. But it's a necessary evil, which most of the time the optimizer can actually figure out that some of the types are the same and can actually get rid of a bunch of these casts, which are pretty great. And that's the same thing when it comes to the actual runtimes as well. This is what that apply function looks like with WASM-GC for us. So on line 3, if you look at those parameters, there were I32s before. Now they're any refs, which is great. Now instead of doing a call indirect, it's a call ref. We no longer have the function pointers in function tables. Now we have just actual function references, and we can call those references that exist in closures, and that makes me very, very happy. And you see we've got these 2 ref casts here. So one is a cast to the closure type, so we can say this is our actual closure type. That one I'm pretty sure we can get rid of from the compiler. I just need to go heads down and get rid of that one. But this one down here is actually calling the function. We do have to do the ref cast here to guarantee to the type checker, yes, we are going to call a function of, in this case, it's 3 arguments because of the closure argument, but otherwise we are going to be able to call that function with those arguments. So that's actually not too bad. That's not too different than this right here. Second major consideration. Grain supports generic structural equality. So we want to be able to have one equality function that can compare a list of things, compare strings, compare numbers, and whatnot, which to do this, we need to be able to walk our data structures, which in linear memory, that's actually fairly easy to do. They're just bytes in memory. You do whatever you like. You can have one function that walks all of them. You can't walk your data structures in WASM-GC. We don't have a way to do that. We don't have any fun reflection-y type things that let you say, hey, how many fields does this struct have, or something like that. We don't have anything like that. And I think that's OK. I think there's a fine limitation. I think we're going to keep that. But this does mean that now we have to do some new things like creating special walker functions for each of our types, which that can maybe bloat code size a little, but it's not something that I'm really worried about. So I don't think it's too big of a deal. But maybe in the future, we might get some fun reflection-y type things. Maybe. Maybe. All right. Major consideration number 3 is that WASI and the component model, as we heard earlier, only work with linear memory. but we don't want to lose support for them in grain because people seem to like that quite a bit. But the fun thing there is that nothing's stopping you from using that linear memory anyway while you have GC instructions. So you can just copy into linear memory when you have to talk to WASI, or in the case of the component model, copy into linear memory to conform to the canonical ABI. What I will say about this, though, is that folks are actively working on implementing the canonical ABI for WASM GC, so you won't have to do those copies anymore. And then, like I mentioned earlier, potentially you can copy things across the component model boundary without actually doing a copy at all. You can actually just say, hey, here's a pointer to that object, and it's perfectly fine. So potentially, the component model could be even better with WASM GC than it is with the linear memory version. And let's talk about some of the compilation effects here. So on binary size, an empty grain program reduced in size from 3K to about 300 bytes. We put metadata and other runtime stuff in every single program. The optimizer can't prove that for an empty program it doesn't need to do all these mutations in linear memory. But with WASM GC, the optimizer can prove that. It can say, oh, I see you allocated these objects and you don't actually do anything, so I can just get rid of them. So that's phenomenal. That made me very happy. Could I have written a better compiler? Yes, but I'm happy the optimizer did it for me. For a Hello World program, we saw a 34% size reduction on that. So that is, we don't have our reference counting implementation in the module anymore. So it's a lot smaller. That's awesome. And then talking about performance, for list allocations, something that's pretty important to us. In WASM time, the GC version is a tad slower than linear memory. The GC implementation of WASM time is fairly new. It's only going to get better as it gets more mature. So not worried about that, but performance is pretty neck and neck, so fine. In the WASM Edge interpreter, the GC version was way faster than the linear memory version. And that kind of makes sense if you think about it, because you're not emulating as many of the just do this thing in memory. So that kind of makes sense. And for something like V8, yeah, turns out they really know how to allocate them objects, baby. Yeah, it screams in V8. That makes me super happy. For Bigint math, we see pretty much the same thing. One thing that you'll notice here is that for the V8 side, there is no bar. That's not because it didn't work. I thought it didn't work when I ran the benchmark because it finished instantly. And it took me a while to track down what was actually going on here. And it turned out that V8 said, well, actually, we don't need to do any allocations for this whatsoever. You're just doing some math, and we can just optimize all that away and just do the math. And so it's dumb fast in V8. So that's some of the nice things. You get so much more semantic meaning out of allocating objects than you do just writing bytes to memory randomly. So to recap, WASM GC makes the implementation of your high-level languages a lot easier. Just create some objects. Nice. Makes your binaries a lot smaller. The fact that your runtime can choose how garbage collection happens is a huge game changer. And the more high-level language that we're able to bring to WebAssembly, because we have GC, just makes the WebAssembly ecosystem that much better. And with the component model, I know folks don't like thinking about it, but we have Python and things like that running in WebAssembly. That's actually a really big deal for us. So the fact that WASM GC is enabling all this is absolutely phenomenal. And with that, thank you very much. Appreciate your time.
Thanks a lot. So we have a good amount of time for questions. Please just go up to the mic.
I'm curious if you have subtyping on function types in Grain and whether that was an issue for mapping to WASM GC?
We don't. So that wasn't an issue for us. I would imagine that it would probably be fine depending on what kind of subtyping you had for your functions. You're just going to have a bunch of casting, which is OK. I don't think it's too much of a big deal. But if you are trying to do something super dynamic, that you could run into a big cost by having to cast that much.
I'll just mention, so Virgil does, and it is an issue for us.
Oh, OK.
Hello, this is a bit of a dumb question, but so you mentioned structs are subtyped by extension at the end, correct?
Yes. Well, you have to. Your first in fields have to be subtypes.
Yeah. So
but then you can add more.
Okay.
things,
Yeah. And then second thing is, okay, so let's say I have a struct field in a struct, or more interestingly, a struct field in an array. I can mark that as final, and then is the compiler generally smart enough to do, for example, like array of structures rather than array of pointers?
Depends on your compiler.
Okay.
Yeah, but so the dream is to have your compilers be able to be smart enough to do optimizations like that.
Okay, yeah. Well, I guess actually...
I don't know if anyone's doing that today.
Yeah, I suppose it might break things if I take a ref to the structure, but I'll stop talking now.
Hey, so thanks for the very friendly presentation of the GC proposal. Well, actually, we shouldn't say proposal anymore.
Yeah, I guess it's done now.
It's done, right? Like, I had one comment, I guess. So one thing you said is that for real time, it's nice that you can switch out the GC implementation as the code producer. You don't have to worry about what it is. I would argue when you do real time and you don't know that it's a reference counting GC, that might actually be a bit of a headache, right? Because it can cause a lot of pauses if you don't know about it. And
I completely agree with you. That's why I didn't say it. That's why I didn't say it. But no, I think that is actually a real issue because I think for people who are using WebAssembly, you are going to compile some module and think that you're fine. You're going to think, oh, I can run this in any runtime and it's okay, but that's not going to be the case. Your runtime is really going to matter, and the type of GC algorithm is going to matter a lot. So I'm hoping we get things like some kinds of hints or things that we can have that say, hey, actually, I do need a real-time algorithm for this, or I don't care, just do whatever you like for this. But I do think that is going to be an issue, but I don't think it's going to be that much of an issue. I think for people who truly care about real-time or other things like that, they're going to know, I'm just going to run a specific runtime that has this algorithm. I think for people, 99% of developers, it's not really going to matter.
Yeah, I mean, especially since if you know your ecosystem, you can make certain assumptions, right? Like on the web, you usually have, I guess, incremental collectors. So
yeah.
Anyway, okay.
Yeah. All right. Thank you very much, folks.
Okay, so I'll get started. Hi everyone, I'm Aaron, a PhD student at the Vrije Universiteit Brussel, and today I would like to present to you WasShadow, which is about developing dynamic analysis but extending a shadow runtime for profit. So I'm talking about dynamic analysis, and really, in more broad sense, I'm using and going to be talking about the use of instrumentation platforms. So an instrumentation platform allows you to develop a dynamic analysis to reason essentially about a target program. Well, at runtime, see how the program behaves at runtime, collect some metrics, monitor the program, potentially even change it. In the context of WebAssembly here, I'm going to be using or focusing on instrumentation platforms that perform bytecode rewriting. So they take the target module, an analysis specification that you provided. It's going to rewrite that program and give you a new instrumented target module that essentially includes the analysis and the original program as one whole, and then you can execute it on some runtime. But the bytecode rewriting approach is sort of like very portable, as in that module can then be deployed on the server side, in web browsers, and in embedded contexts. Now, instrumentation platforms, there exist multiple. Wasabi has been used, for example, in a previous talk that was given today. I'm developing Wastrumentation, and there's also WAM, which is also going to be presented tomorrow. You can develop the analysis in a high-level language. But as part of my talk, I'm going to be focusing on instrumentation, as I'm the developer behind instrumentation. You can use any high-level language that compiles down to WebAssembly, and then instrumentation will sort of merge that analysis inside of the target program. And I'm using my framework as it maximizes analysis portability. You use a high-level language for the analysis, and it also supports intercession, which is going beyond observing the program, but also mutating the program. So if you look at how you define such an analysis in instrumentation, but the idea is generally generalizes for the other frameworks too. You sort of have two key components. First, you have to tell the instrumentation platform what the target events of interest are. And then secondly, you sort of implement the analysis logic as a sort of callback. I call it trap functions. And then at runtime, when you deploy it, the instrumentation platform will make sure that your callbacks will be invoked for set events that you are listening for, right? So for example, if you would want to hear, what you can see is you're listening for binary events, and then the callback receives as arguments the operator, the left and right operand, and then the static location in the binary of set event. So for example, you could write a tracer in instrumentation of all binary events by replacing line 5 with a log statement, just printing out what's happening, and then at runtime, you will get sort of this trace of all the binary instructions. And so for example, in instrumentation, you're also in control of the outcome of the offset operation. So you can see on line 4, sort of you compute what is the outcome, and then on line 6, you return that result. So you could also, if you want to, mutate the argument as part of the analysis. Now, what I want to discuss here is this analysis API, does it provide sufficient information? So the trap functions, they receive the event information as arguments. So for example, for the binary, it was the operator, operands, and the static location. This approach, from developing an instrumentation platform point of view, is lightweight. For the analysis user, it's easy to understand. For the author of the platform, again, it simplifies also the instrumentation path, makes it easier to reason about, but it's very event local. You only get this information, right? For example, you're missing information about the state during execution. State being the execution value stack, global variables, their state, or linear memory. Sort of, you miss this reflective API. It's available for the VM at runtime, but in this portable sense of developing analysis that should port to different runtimes, you cannot really access this information from the semantics, right? For the WebAssembly binary, this is not exposed through the semantics. And this sort of comes as a limitation, because if you're then implementing portable heavyweight analysis, they are starting to reconstruct this state. And I noticed that they do it in an ad hoc fashion. So Wasabi is one of these frameworks. They have a taint analysis implementation, and somewhere they start to model this state. And you can see here in the comments that they have like a fix me, sometimes pop returns undefined, and not just an empty list. Why? So they implemented a hacky workaround to sort of get rid of a runtime error. Now, to overcome this, I sort of want to do it the other way around and implement a dynamic analysis framework that models this information for you. So then I come to Shadow, which is a shadow runtime analysis framework. And so you can see on the left-hand side that sort of your analysis will extend this shadow runtime implementation using that much more information available to then reason about the program's behavior. Now, to understand the implementation, or how did I implement this dynamic analysis, I went to the spec, the WebAssembly spec, then, and I sort of started implementing this, the specification or the execution, how to execute WebAssembly programs. So, for example, for the binary operator, you can see that the semantics says on instructions 2 and 3 to pop the values from the stack, and in instruction 4, you compute the binary outcome and push it again on the stack, right? So I took this implementation, implemented in the binary trap of instrumentation, and so you can see sort of this parallel that, again, you have like in comments, I sort of copied over the semantics of the specification. So I popped the 2 values from the shadow stack. I also, in between popping the values from the stack, I assert that what my hook receives, or what this trap function receives as a runtime argument, matches with what the shadow stack is modeling. And then eventually I compute the outcome, push it again on the shadow stack, return it to whoever called into this analysis code, and I continue with the execution. But this sort of makes all of these this runtime information, the state of the program, also available for others who then build on top of this framework. I did the same for others, so you can always see there's like a parallel between the WebAssembly specification on how to execute a certain instruction, and then the implementation on top of my framework instrumentation. And you have the same for if then else. There's always this parallel. Sometimes it gets a little bit large. You should not be reading this really, but you can see there's always like this parallel correspondence. And then on top of this, we built a few more interesting tools that sort of make use of this information, right? I'm going to be showcasing three, one of which is JASMaint, then WASM, and then Shadow Shell. So the first one is JASMaint, right? And to introduce JASMaint, this work has been developed by a bachelor student in the context of his bachelor thesis, Abel Stucker, this year. And what he did was he replaced the domain of shadow values to the domain of shadow taints. So in this implementation, every byte has been replaced with either a tainted or untainted value. And so then the shadow stack, the global store, linear memory, it all keeps track of not shadow values, but just of the taint that corresponds to what that value would otherwise capture, right? So for example, for an add instruction, to propagate taint of the two arguments and compute the tainted result of the outcome argument, you take the taint field of your first operand of your second operand, and then you sort of like logically combine them with an OR operator to compute the taint outcome of the result of that instruction. And same goes for linear memory. So for example, if you have two store operations, one of a tainted value, another of an untainted value, if you both store them into linear memory and then load them again from linear memory, but then for a larger value size, then you effectively transfer that shadow taint to keep track of the taint of all the values flowing through your program. So in the implementation, we combined the shadow taint analysis for WebAssembly together with a taint analysis for JavaScript and composed like a unified framework to track taint across interoperating programs between JavaScript and WebAssembly. And as part of our evaluation, we could show that using taint tracking also in WebAssembly with respect to just taint tracking on the JavaScript side and treating the WebAssembly module as a black box, that you could reduce over-tainting values down to 44%. The rest of the details were shown and are still present in the paper that we presented at the co-located MPLR conference. So the second showcase is WASM, which is developed by Nikita Servet in the context of his master thesis. And so here the idea goes that you have a target program developed in a high-level language, Rust or C, any other. You give it to a compiler, and it can provide you an output module, but also the debugging information, if you ask the compiler with the right flags, the debugging information for said program. And so that debugging information is then used whenever you deploy that target program on a runtime to talk from an external tool to a debugger backend. It's going to read the debug information, and that debug information explains sort of how to reconstruct the high-level semantics of a program. So, for example, the debugger backend can explain, using that debug information, what values are currently in scope. For example, if you set a breakpoint at an if statement, what's currently in scope according to the semantics of that high-level language, what are heap allocated values, and how should you interpret them? For example, is it a character pointer? Does it point to an integer? Or a more complicated data structure? And also, for example, the globals. They could be mapped to either a static global constant from your high-level program, but it could also, for example, be used by the runtime to represent a stack base pointer. So to reinterpret that debug information, the debugger backend allows you to reconstruct that state using the debugger info. However, such a debugger backend should be provided by every runtime, right? WASM ships their own, V8, Firefox. Say a new runtime comes along, runtime X, and they provide a novel debug feature Y. Another runtime comes along, a WebAssembly runtime, runtime Z, which does not have a debugger backend, right? Then you can sort of see that novel feature cannot be explored in different contexts, does not port to different environments, nor can you actually use that debug information on runtime Z. So what if we then, as part of the WASM, lift that debugger infrastructure as like this portable debugger backend that you can then deploy in different contexts. And so we use WASM and WAShadow analysis to sort of build this portable debugger using that the entire state context to build a portable debugger. So I can demo this also. So what you see here is I have a C program in which I have a factorial function. And that factorial function is recursively defined. So the argument is 0, return 1. Otherwise, you call recursively factorial with the decrement of the set argument multiplied by n. And we expose the function computation to compute a factorial of 5, add 3 to it. So the result should be 123. And the main also invokes the computation. So if you build it and pass to mscriptum the flag G, you sort of get this output debugger information. And then what you can do is you can execute the program on wasm time, and hopefully wasm time, returns 123 as expected. However, if you then use wasm, you sort of can ask it to, given that binary information, also output a debuggable binary. And then that debuggable binary, so I'm sort of passing it also some source files because the debugger wants to also read those files. Then you can invoke the debuggable binary, and sort of this debugger can pop up. You can ask it, what can you do? You can continue, set breakpoints, step to next instructions. So I could just say, okay, step, or in shorthand, hit S, and then it walks over each binary instruction and eventually walks through the program. There's quite a lot of instructions at the binary side, but you can then see the debugger walk that entire program. So I can also set breakpoints, and set breakpoint here, set a breakpoint on line 7. So sort of like at line 5 and 7. So in both return cases, I want the debugger to stop, and then I could continue through the execution and then view what is the value of the current variable in scope, n, which is should be interpreted as a 32-bit integer, is now value 4. Let's continue, it's 3, 2, 1, 0, and then eventually it should return, and that's 1, 2, 3. So you have this portable debugger, but the idea is that you cannot only run it in wasm time, but then, for example, also in wasm edge, right? So an engine developed in a different language, not C, but not Rust, but C++. It takes a little bit more time, but eventually you have sort of the same functionality in which you can set a breakpoint and then continue to the execution. It takes a little bit more time, but eventually you reach that same functionality, right? What I can also do is I can compress the source information. Let's bash. Let's compress actually just the directory of the source code, and then I get an archive C, which just holds the folder of the source code, and inside one file, which is that source code, and then I can. Also go, for example, into the web browser, load that same debugging binary, load in the virtual file system, so pass the files to WASI. Great, so that's there, and then sort of like hit run, and you get that same debugging experience, but then it doesn't run on wasm time, wasm edge, but also on V8 in the web browser, polyfilled with the WASI playground. Funnily enough, it cannot access certain files here, like it would love to have the scriptum source code present, but eventually if you keep on stepping, sort of the files that are present in the system can be read and can be showed in that debugger on the client-side engine. Then, let me just continue. So something else that I then built was a shadow shell. So there the idea is, what if you have a REPL and just can hook to a running instance at runtime to explore how that program is behaving or what it's doing. So for that demo, what I prepared was, if you go to WASM 4, WASM 4 is this project where it's this virtual console where you can play video games. So for example, you could play like a Tetris clone, which has been developed in Zig, I think. But what if this source code was not available, right? You just want to attach yourself to the WebAssembly running instance and explore the behavior of that program at runtime, just at the level of WebAssembly. So I built this Chrome extension in which I ship like a pre-compiled analysis, this shell environment, together with the instrumentation itself. So compile all of that to WebAssembly, and then on the fly instrument a program. So let me go to that game here. Okay, reload it. Great. And so then you can have this little scripting environment, which I have on the left. So I can write an expression like 10 plus 20. I get then the output 30, or I can write it as a string, and then it just displays the string, right? So what you could do there is like reason about this reconstructed state. So for example, say I'm really bad at Tetris, but and I really want to get that to see what the score is. What you can do is you can pause the game, and I provided this stateful function which is like based on to scan the memory for 32-bit integers and to see where are those indices of 32-bit integers. So for example, to go to scan for the value 0, that gives me a memory scan, and then what I can do is I can display it as a string, and it says, well, currently linear memory is about 16,000 bytes, and about 16,400 bytes of that, of 16,400 indices match to the value 0 if you would interpret them as a 32-bit integer. Now, currently my score on Zictris is 11, so let's see if there's values that match the value, if there's any 11, and apparently this index matches if you look at that byte and interpret it as a 32-bit integer, that's an 11. Let's see, okay, now my score should have increased because, or let's increase it to 27 now. Let's see if 27 is, so let's reduce the previous set. So reuse the previous set, but see if now the value has, any values change to 27. So apparently it still gives me the same value. And now I can use the intercession feature of instrumentation to ask it to overwrite the value, right? Can I sort of like put there a very high score, right? And it says override performed, so would it be reflected here? And apparently I hacked my score. So without looking at the source code, but reasoning about how one would implement the program, you can actually hack a little bit, play around with such values, and produce quite cool tools, I think, right? You also have another option, which is, I think, save or store. No, okay. I forgot the function name, but I wanted to store and restore linear memory, but it could not. Then it just crashes, which is quite funny. This is like low-level hacking around in a WebAssembly file. It doesn't always work. It's quite dangerous of a practice. But let me get back to the presentation. I think implementing, so I packaged it as a JavaScript, and essentially I hooked into all of the WebAssembly instantiate, compile, instantiate screaming hooks to sort of replace getting that module, rewrite it on the fly, and then deploy it again. I think using such a shadow runtime sort of can help validate the instrumentation platform. So, for example, I inject many assert statements. If one of these assertions breaks, either the shadow execution, the instrumentation, or the VM that you perhaps are developing, or the compiler, one of them has a bug, but it can help to sort of evaluate also this entire tool chain. This is ongoing work. I would like to not just fork the shadow execution and build these tools, but see if I can provide hooks on that sort of meta level. And also the runtime overhead is quite high, so exploring how you could reduce the introduced code would be a nice feature. Thank you for coming to my talk.
Thank you. Please line up for questions. Our next speaker is a remote speaker. Can we get them connected now as we do the questions?
So one of the things with WebAssembly is, sometimes you just get like a binary and you have no idea what it is. And one of the things that's a bit difficult I found is sort of if the thing is written incorrectly, then like in particular with manipulation, like a sort of memory safety problems in the linear memory. then it's very difficult to detect because there's sort of like, there's no structure to it in a sense, right? In the memory. Have you tried using this instrumentation to sort of add sentinel values so that if a part of the program tramples another part, then you can detect it? And if so?
No, so that's a type of dynamic analysis that I haven't implemented, but I think certainly it would be feasible, especially if you can reuse this debugging information. You can sort of even reason about what assertions should hold at a source language.
So
and
maybe I'm wondering, right, because you said you sort of instrument the thing. One thing you can do is instrument next to every value, you put sort of a sentinel thing so that when it gets overwritten, if you're lucky, you see that the value has changed.
Oh, okay, yeah. I haven't explored that, but it's an interesting instrumentation attempt that I could try, yeah. Thanks.
Thanks, Nico, one more time. Okay, we now have a remote speaker ready to go live. This is Jerome Goulin, I hope that's correctly pronounced, on dynamic multimedia pipelines for opening browsers with new formats. Please take a look.
Hello, can you hear us?
Yes, I can hear you.
Okay, perfect.
Them up a bit, it's a little quiet in the room.
Are we ready?
Yeah, we should be. All right, whenever you can.
Okay, thank you very much. I am Maya Bystrom, and together with my co-author Jerome Gurin, I'll be talking about dynamic multimedia pipelines for opening browsers to new formats. Now, this is a bit of a diversion from some of the work that we've heard earlier today, and that we're going to be talking about applications of WebAssembly and some of the tools we've developed to make the applications more feasible for novice users. So let me turn immediately to the problem that we're addressing, and that is there's a host of multimedia formats out in the world. Here's a snapshot from Can I Use of two popular ones, OGG Theora video and JPEG XL image format. And what we see are that these are not universally supported, and in fact, browsers have been adding and dropping formats at will. So what this means for people in the multimedia field is that there is a great deal of content already produced in these formats. So how actually should we handle content that's been produced and stored in these formats? And also, there's a great deal of uncertainty that puts barriers for format developers. How do they know that they'll be able to use their format within things like web browsers? So we are addressing this problem, as I think must be obvious to everybody here in a WebAssembly workshop, by inserting a decoder or transcoder built in WebAssembly between the legacy or brand new formats that are not supported by certain browsers. Our WebAssembly transcoder or pipeline will take for instance, legacy MPEG-1 video, and using wrapper, written also in WebAssembly or JavaScript control code, and convert it into something that is more universally supported by browsers that can be easily displayed by an HTML video or Canvas element. So that while this may be obvious to all of us, the challenges lie, first of all, in building a WebAssembly pipeline, so a WebAssembly decoder or transcoder. And although it's clear that with the help of everybody in this room, that great strides are being made toward making WebAssembly more accessible to developers, it's still going to be a challenge, I think, to folks who really focus on format development or even website development. So the key challenges we see are being able to generate a multimedia pipeline on the fly. And we do this for a number of different reasons, including flexibility and code reuse. And also we generate pipelines really for adaptability. Pipelines are composed of subcomponents, and you can put in subcomponents at will to test out new formats or to perhaps deal with optimization for certain platforms, or even in terms of dealing with intellectual property issues, you may want to switch out subcomponents. Once I discuss a multimedia pipeline, then I'll talk a little bit about how this relates to implementing within websites. And we want to make sure that it's easy for both site developers, format developers, everybody who has to work with multimedia to be able to handle it and the WebAssembly components very easily. So I'll review 3 different types of approaches and show some demonstrations of performance. And along the lines of performance, I'll show you some of the hard performance numbers that we have been coming up with. So let me start by focusing what is a multimedia pipeline, and this may not be as familiar to many of the people in the room. But a pipeline is a algorithm broken up into multiple elements. Each of these sub-elements is linked. We might call them filters or sub-algorithms. The pipeline is unidirectional for a transcoder pipeline, which is what we're seeing at the top of the page. We would have an input element, a demuxer element, in the middle, a decoder, and then a re-encoder, and then off towards the right, a multiplexer, and then an output element. The reason we want to build these on the fly rather than having a really static, monolithic, precompiled element that we could insert in a web page is that, as I said before, it gives us a little bit of flexibility. And the way we build them on the fly is that we would take input data, in this case, OGG video as shown on the right, insert it into a main module. We'll call this one Solver Generation 1. And Solver 1.1 Generation 1 will take the video and a whole set of side modules, and using a little bit of optimization, resolve the pipeline with these given side modules. And notice that the side modules can consist of things related to this certain type of video, Vorbis Theora, as well as a host of other side modules. So I've included in there a JPEG XL side module, and it could be a wide range of side modules handling a vast set of different types of video. So the main module dynamically links the side modules in the pipeline and then efficiently executes the pipeline. Now, moving on to how we would ensure that this can be implemented in a website very efficiently, let me first turn to web components. And I'll also, when I discuss each of these, I'll, as I advertised earlier, show demos of this from a showcase that we have produced. So starting with web components, web components is really familiar HTML notation. It lets us reuse HTML elements and extend them using additional attributes. So here we see a traditional HTML canvas element. We've extended it using a universal canvas, and we can see additional attributes, including the main module solver, a restricted set of side modules, and then the input data stream, which would be an OGG container. So the universal canvas, here written in JavaScript, would read in the data that we want to display on our page, instantiate in the WASM instance. Solver would then perform its magic by resolving and creating a pipeline and then running the trailer 1080p through the pipeline to produce both the video out and the audio out. So let me show a demonstration of this in action. We'll go to our showcase, and you can see that this Big Buck Bunny trailer automatically plays. So it's stored, as we showed before, in an OGG format container. And then if we take a look at the inspector, you can see the web components that produced this particular video. Now, I'll also show you a JPEG XL image in action. Again, here we see the image tag, and if we go on to inspector, you could see that we have extended the image tag with universal image, but again, are using a solver and a libjxl precompiled WASM library component. So web components is very familiar, and it gives a lot of power to a format developer who might want to do testing and development. However, it's not very transparent in the sense that you have to understand HTML and have to track your attributes and so forth. Second example is a mutation observer, where you would use standard HTML, and a mutation observer is an interface that provides the ability to watch for changes being made on the document object module tree and react to them. So in this case, the mutation observer on a decoding failure would divert to a decode function, which then has to contain the main module solver and an entire set of side modules. So obviously, this approach requires a decode wrapper that can actually be complex because it has to handle a vast variety of multimedia that might be used in any particular site. However, when released as a monolith, it's very transparent to a user or a site builder. A little less flexible for folks like format developers, though. However, let me go ahead and again show you a demo using our showcase. Here we again are seeing the JPEG XL image, and you can see highlighted in Inspector that we have where you just use the simple, straightforward HTML specification of image source, but we do have a mutation observer that sends this data to the image decoder. And the same thing happens for audio as well as video. Okay, the last example I'd like to talk about is Service Worker. And in this case, we are reusing a container, in this an MP4 container in this example. And this container has both the embedded HTML, so the web components approach that we saw before, the main and slide modules, as well as the raw data. So we know that service workers are really specialized JavaScript components that work as proxies between web browsers and web servers. In this case, we're using the JPAC MP4 box service worker. And what that will do is extract the web components portion. And note that this looks very similar to what we saw before. However, I've also added the attribute that we will be using web codec. It extracts the main and side modules, runs the solver and the ISO-BMF MP4 handler, and sends the raw data down to web codec. So that is an API that lets you use the underlying codec control from the browser. So I'll quickly show you, hopefully, two examples from service workers. Again, we'll start with a video trailer. So we see that the trailer is packed in an MP4 container. Once we click on this, we'll see that the MP4 container, or we'll realize the MP4 container is unpacked, pipeline is built, and the service worker has sprung into action, and the video plays very quickly. Now going to a different example, I'll show you 360 content. Again, we see the web components HTML up on the right, and you can see the interactive nature of the 360 content on the left. So I'll go very quickly over a little bit of performance considerations. So Service Worker is very transparent to a user, however, puts a burden on the designer who is going to be packing all of the data and all of the side modules and main modules into the container that's used. So we really have to consider how big our main modules and side modules are. And in the cases that I've demonstrated, they're actually fairly reasonable. Quickly thinking about speed, if we look at the table in the lower left, if you think a few slides back, only Safari natively supports JPEG XL display. So using the Zoltan image, we've measured a 17 millisecond decoding display time for this particular image. Our pipeline approach, because it includes the pipeline creation, instantiation, et cetera, as well as decoding, is significantly slower than native decoding. However, it still is at 100 milliseconds, and hopefully our demos convinced you that this is useful. Okay, the same thing happens in the video case. Quickly, we are able to offer a very satisfactory 67 frames per second at for a large image size, 1080p. And compared to a JavaScript solution that is cross-compiled into WebAssembly, we are just slightly slower, and that's due to our pipeline construction. So hopefully this is a little bit convincing that WebAssembly is providing us a fantastic application for multimedia developers, content providers, content hosters. For anybody who wants to take a closer look at what we demoed, I have the link up at the top of this page. For anybody who's interested in looking and assisting, I provide a lot of other links to our open source resources, and I'm now happy to answer any questions.
Thanks so much for the talk. I appreciate you might not be able to hear the room unless I speak directly into the mic. We've got some questioners lined up now, but thank you again.
Thank you.
Hi, my question is, so you had shown the full time to render included the instantiation time of the WebAssembly module and whatnot. Do you know how much of that is the instantiation time? Because assuming that that stuff is preloaded, I imagine it's probably not actually that bad.
No, well, I think getting a little bit of feedback there, but no, it actually isn't that bad. And I can invite my co-author, Jerome, who actually did the measurements, and see if he has anything to add to that. I think Jerome is unmuted. Okay, I don't think we can hear him, but no, I'm sorry, we can't hear him, but maybe I can answer the next question, and anybody who has additional questions and thoughts can feel free to reach out to either of us directly.
I guess I have one question. You talked a lot about how the existing features of the web, like service workers, are allowing you to do a lot of good things. Are there any big missing features that you'd be interested in us adding, given you have some of the standards body in the room here?
Well, given that we have some of the standards body in the room, we would love to see some of this standardized and incorporated, so we didn't have to include service worker on the pages. We'd be thrilled to have even something like our web components standardized, just to make things easier for all of the folks like multimedia developers, and not just multimedia. This is useful for really displaying any type of data within browsers.
If you did keep on using this strategy, are there any core WebAssembly features that you might think might make it easier for you?
Certainly. It's 2:30 in the morning my time, so off the top of my head, nothing is immediately coming, but we are certainly happy to get back to the room with those. There are, yeah. And
all good, thanks for that. We have one more question lined up.
yeah.
Hi, I'm not really a WebAssembly guy, but I've been doing some work with video in the last years, mainly with GStreamer. And I think I can do in GStreamer is make my own element to put in the middle of the pipeline to, for example, I don't know, do a YOLO inference and then that will pop out frames directly with YOLO. Is that something I could be able to express in your approach?
Yeah. So things are, so again, I blew through the pipelines very quickly because I didn't think that was so much of a focus of this audience. But really, the pipelines are flexible that you could, really develop anything that you want within them.
Thank you.
Hopefully I understood and answered your question with that, yeah.
A similar abstraction as GStreamer as elements or beans, for example.
Right, yes, yeah.
Okay, great, thank you.
Great, thanks so much. We're going to thank you one last time. I don't know if you can hear our applause or not.
I can't, but thank you to the audience.
Great, thanks. We're going to switch over to our next speaker now. Thank you so much for joining us. this session, we have Maxime, who is going to be talking about... Oh, I'm so sorry. I realise you won't be able to hear me unless I speak in the mic. For our final talk of the session, we have Maxime presenting remotely about Iris WASM. Thank you so much, Maxime. Please take it away.
Great. Is my screen showing up now? Am I in full screen?
Yes, you are. You are good to go.
Okay, amazing. I am seeing something else on my screen here, but I'll just trust the process and just go ahead. Hi everyone, my name is Maxime, and I will be talking today about Iris WASM, a framework to reason formally about WebAssembly that we've also used to reason about extensions of WebAssembly. I'll give a big overview of the project, and I'm not going to get into any technical details today. But I'll try to explain what we've used this project for and what our motivations were in defining this. To start off, I would like to take a short second to remind ourselves why we even endeavor to reason formally using proof assistance. That's probably going to be very obvious, but I think it's useful to keep this in mind. A proof assistant obviously is going to be deliver much better results than other techniques like testing. But what is it we're trying to achieve here? I think there are three main goals when reasoning about a programming language. The first one is that you're going to be able to find bugs, typos, imprecisions, places where you need your language to be completed. Because if you've ever used a proof assistant, you know they're very unforgiving. You need a complete proof, and you won't get away with any shortcuts, any missing edge cases. It's also going to force you to define absolutely everything for your entire language, and so you need to have definitions that are precise and that are complete. But even if you are in a case where somehow maybe you've done extensive testing and you're confident in the fact that you aren't going to find any bugs, having these kinds of formal proof is going to encourage people to use your language, because now you're able to define very precisely what kind of properties your language brings. And you're going to be able to prove those properties to a level of confidence that is not possible by mere testing. And then the third point that I have on my slide is here that you're able to verify code in your language, which I think is what most people think of when you say that you are defining program logics for a large language. And obviously that's something that's very valuable, but to me, I like to remember that there are other important reasons why we do this formal work. So if there are all of these advantages to doing formal proofs in proof assistance, why are we always doing that? Well, obviously the largest drawback in doing formal reasoning is that it is a huge effort, which requires expertise, it requires time, you need to define everything. You need to know how to formulate mathematical proofs, and you need to know how to do all of those proofs. That takes time. It's not a resource that you always have, which is why you don't always get to do this kind of formal reasoning. But we argue it's really valuable. And one language where it is as easy as it gets to do formal reasoning as compared to other traditional languages where this defining a mechanization of the entire language would in itself be a very tedious step, is WebAssembly, which obviously today I don't need to introduce, but what I'd like to say is what I love about WebAssembly is that it strikes its balance between being a language that is both very widely used, it's not a toy language, it's not an idealized subset of some language that I use to do research, it's an actual thing that people care about. But it also has this full formal specification that makes it relatively more easy to do formal verification on. And that's obviously something that's big in the spirit of WebAssembly, that's why it's been defined this way. So the starting point in my work has been that we realized that code in WebAssembly is organized in modules, and people care about those modules not being able to arbitrarily interact with one another. What I mean by that is that I don't want a module to be able to meddle with another module state unless that other module has explicitly marked something as exported, as shared. And we were wondering if we could formalize this in a proof assistant as a universal contract, and the strategy we've used is to use separation logic. We have used a framework called Iris, which I'm going to show a tiny bit more of how that, what it exactly looks like in practice. But the idea is that Iris has an implementation in the rock-proof assistant. If you're able to describe any programming language in the rock-proof assistant, then Iris provides you with a logic, a set of program rules that you can use to reason about the behavior of code in that language. And we've asked ourselves whether or not we could use this on an industrial-sized language like WebAssembly, and that's what we've done. We've defined Iris WASM a couple of years ago, which is an instantiation of Iris for WebAssembly. I'm going to show very quickly how that looks, what that looks like in practice, but the big picture is that we have a program logic that you can use to reason about code in WebAssembly. That is the full industrial definition of WebAssembly 1.0. We haven't got 2.0 yet, but that's something that we could probably achieve as a future work. There's one small departure we've made in the way that WebAssembly deals with host calls that was ill-adapted to a mechanization. But apart from that, we're sticking exactly to the definition and not to an idealized subset. We have a logic that is higher order, so you get to have proofs that are very, proofs of very general statements. The logic is modular, meaning you can reason separately about different functions or different modules and then compose all of the works you've done together to reason about entire traces of execution. We model reentrancy, meaning you can call the host, the host can call WebAssembly back, and you can have these kinds of complex interactions between the host and WebAssembly. And we've defined a logical relation that goes hand in hand with the program logic that allows you to reason about unknown, untrusted code. It's what we call robust safety. And what that means is basically if you are making a call to a function that you don't know, say a library function to a library that you don't trust, you're still able to say some meaningful things about that interaction. How that looks like in practice is that I have resources in my language. These are these little arrow statements that I have on screen now. I have a resource here for global variables that says global variable G points to 42. I've written WG on top of my arrow to indicate that this is a WASM global variable. And likewise, all of the elements of the store are going to have an associated resource for the memories. It's noted with WM. And what I'm reading here is that the memory number M in the store at address specified by the subscript here is pointing to the byte 47 or whatever the byte might be. And then we can write proofs that are going to look like this. If I know that that my variable G points to 42, then I'm able to run this short program that just gets the value of G. And I know that when this program returns, I'm going to get value 42, and I still own my resource, so I'm able to further reason about G later on. In the most general form, it's what I have here at the very bottom of my slide. If I have a precondition P, this implies with the one that is separating the implication that we use in separating logic, I have the weakest precondition for my program E, and that means that my program E runs safely. It does not get stuck, and if it returns, then the value V on its the return value V satisfies its predicate phi, and P and phi are going to be phrased using these resources. So that allows you to reason about code, to verify code if you'd like. And then the most important result that we have is this logical relation that we've defined, which is a mathematical object that is defined in a proof strategy in order to prove these kinds of very strong properties. And the property that we've proved is that if a program type checks syntactically, which is something that is in practice always achieved because instantiation will guarantee this, then whatever inputs I give it and whatever imports this program does, as long as I'm able to verify that these inputs are valid in a way that I would need to define, then I'm going to be able to run E with those inputs V, and I'll terminate on a value that is also valid. And what this means is that I need to provide resources to indicate that all of my imports are valid, an unknown function, and there is a part of my store that I have not marked explicitly as exported that is not going to be an import of that unknown code, and that means I'm able to know that that code, that unknown code, is going to run safely, not get stuck, and I don't need to provide that that value. So this formally captures local state encapsulation and is a very strong formal proof that WebAssembly has that property. Now, obviously, WebAssembly we've been using for years now, and so maybe there wasn't too much doubt that WebAssembly has this local state encapsulation property. But the thing that we're most excited about with IRIS-WASM is that now we can use it as a departure point to reason about new variations of WebAssembly that maybe we don't know as well as WebAssembly. Maybe we don't have as strong confidence that these languages have whatever properties we'd like them to have. Oftentimes, when you create a new version of WebAssembly, you can think of it as the intersection between WebAssembly and a new feature. And because Iris is, just like WebAssembly, a very vibrant research ecosystem, that new feature has oftentimes already been studied in the Iris program logic. So our thought was that maybe we can, in that case, try to massage together all of these existing projects to get a program logic, a logical relation, establishing a universal contract on those new versions of WebAssembly, on those new extensions that we are now saying interesting things about, where maybe it wasn't as clear as before. I'd like to stress here that even though I have this presentation as a Venn diagram that might make it look like this is as simple as taking the intersection of existing works, there is a lot of work involved in actually making this work, as probably should expect it when you're working with these large industrial size definitions. But we argue it's worth it because everybody in this diagram will then win something. For the WebAssembly community, that's what I mentioned at the beginning of my presentation. We're going to find bugs, we're going to validate the design of our new extensions, and we're going to encourage people to adopt these new extensions by telling them exactly what they're getting out of it and giving them the strong confidence in the properties that they are getting. The Iris community, from the logic perspective, gets to see the logic exercised on a very large scale and highlight some needs, some things that work, some things that don't, some things that should be improved. And then the new feature community gets that feature studied at a real life scale. And here I'd like to conclude my presentation by giving 3 examples of how we've achieved this in the past on extensions of WebAssembly. The first such project was Iris MS-WASM, an instantiation of Iris and an extension of Iris-WASM for memory-safe WebAssembly, a version of WebAssembly that uses capabilities, hardware capabilities, as a way to access memory. Instead of having a pointer, I have an unforgeable token of authority that allows me to access memory. And what that means is that all of a sudden I'm able to share at a much finer grain. I don't need to share my entire memory or nothing. I can share specific locations because only people who hold a capability which cannot be forged, cannot be accessed by unprivileged operations are able to access my memory. So we're able to provide a full mechanization of the logic, a full program logic, and a full logical relation that encapsulates a much stronger contract, which is robust capability safety. So if I look at my theorem from before, I have almost the exact same phrasing here, except my definition of this V is a bit finer, which means that when I say that I need all the imports that my unknown, untrusted program has access to are valid, this means that I need to provide them with resources for all of the specific addresses that they'd like to import, not entire memory. So we have a much stronger property here where you're able to share at a finer grain. And this is a work that we're really excited about because MS-WASM is not something that has been extensively tested yet. And now we have some formal proofs that some of these things actually work and a formal statement of exactly what it means that we have this stronger safety guarantee. Another work in progress that's nearing nearing completion is Iris-WASM effects and an extension of Iris-WASM to stack switching, the version of WebAssembly that has effect handlers. And for that, we've taken inspiration from an existing logic in Iris called Hazel. We've now defined a full mechanization of the language with a proof of type soundness, and we've been able to define a modular program logic, which is a big deal when you have effect handlers because it means we're able to reason about functions that do perform effects in isolation and then compose all of our proofs together. And the way we've done this is by introducing this protocol in our logic. So we have a slightly more complicated weakest precondition statement here that takes into account when I'm performing an effect, I might not be able to reason modularly if I don't treat the effects separately. The last work in progress that is using Iris WASM is Iris Rich WASM, an extension of Iris WASM for a version of WebAssembly that has a richer type system, which allows us to have some much finer grained proofs, especially when you're reasoning about the interaction between a GC language and a manually managed memory language. If you have these two languages interacting, you could compile them both to Rich WASM, and then Rich WASM compiles down to WebAssembly, and we're trying to use Iris WASM to prove safety of that kind of a compiler, which is a very exciting work, and that we look forward to bring to completion. To conclude, Iris WASM shows that machine check proofs are possible even on languages like WebAssembly that are industrial scale. And we would love to see a lot more of that because of all of the positive things that this kind of reasoning brings. We think Iris is an ideal tool to do this, and in the case of WebAssembly in particular, we think Iris WASM is an ideal starting point when you'd like to reason about these extensions of WebAssembly. Two works in progress are the works I've just mentioned on stack switching and on Rich WASM that are at various stages of completion. In a maybe longer term future, we'd like to investigate how Iris WASM could work together with SpecTech, or would we be able to use a kind of automation that SpecTech allows and brings to the table while doing these kind of formal program logic proofs in Iris WASM. Here's the Venn diagram again on exactly how Iris WASM works and how you're able to get this trophy in the center in order to boost your own exciting new variation of WebAssembly using formal reasoning tools. Thank you very much.
You may not be able to hear it, but we just applauded you. So
thank you.
A little into the break time. Maybe we'll have one or two questions if anyone has something they'd like to bring up. I have one question. Iris is famous for doing concurrent reasoning. Clearly, you're not modeling concurrency in WASM yet. Have you looked at that at all?
So Iris is famously a very powerful tool to reason about concurrent logic, but there are a few examples of Iris being used to reason about sequential languages as well, and this is certainly a big one of those. In the future, if we were to reason about a concurrent version of WebAssembly, in that case, we already have all of the machinery in Iris to reason about that, and in the stack switching project where we reason about Iris with effect handlers, we have used this machinery in order to reason about examples where you would emulate concurrency using effect handlers. So we have an example illustrating Iris WASM effects that implements a coroutine library where you would have this kind of concurrency, and it has come in helpful that we already have a number of works on how you would use Iris to reason about those. We think that's definitely a strength for Iris WASM moving forward.
That's great. Thanks so much. I think we'll go to the break now, but thank you for joining us, Maxime. Let's thank Maxime one last time. All right, we're now going into our break. Thank you for joining us, Maxime. to our final session of the WebAssembly workshop and our final keynote speaker. Last but certainly not least, we have Chris Woods talking about software engineering economics for runtimes with a code name that I'll let him explain.
It takes a long time for me to get to the point, so in this talk I'm going to start in 1987. 1987 is a big year for computer science. It's the year that Windows 1.0 was released. It's a big year for culture because it was the first time we ever saw Bart Simpson on TV. But most importantly for this talk and this story, it's exactly 10 years since the release of Star Wars. George Lucas, its director, is now quite wealthy and very famous. And at the time, he decided it was the right moment to enter the computer game industry. So creatively, he came up with a game studio called Lucasfilm Games, and we now know it as LucasArts, and it's part of Disney today. He said, look, we're going to create a game, and I'm going to challenge the LucasArts games team to create a movie-like experience with a home computer in 1987. I'm not too sure if this computer game thing's going to work, so you can't use any of my IP, which means you can't use Star Wars. So create your own story. And you have to make money. Now, to make money in a home computer game in 1987, you don't target just one computer, you've got to target a range of them. And what the team faced was something that looked a little bit like this. The most popular and cheapest and most prolific home computer was the Commodore 64 with a whopping 64 kilobytes of RAM and an 8-bit microprocessor. And we'd had the Apple Mac II being released at the other end. The goal was to release a game that could address all of these platforms. And that's going to be a bit of a challenge. They did actually do it. And in 1987, they released the world's first point-and-click adventure game called Maniac Mansion. It's a comedy horror. Basically, a mad scientist kidnaps a girl, and 4 young friends have to go and rescue her. Traditionally, if you're going to create a computer game, you would want to target that small home computer first, the Commodore 64, and you would write your game in assembly. Sounds quite problematic if you're going to try and introduce things like plots and character development and puzzles. This, to give you an idea, is what Hello World looks like in Commodore 64 assembly code. Not the easiest one. So the team went away and said, you know what? We're going to create a runtime and a programming language. And they created the script utility, or script creation utility for Maniac Mansion. And it solved the problem. It ran on a Sun workstation. And it allowed them to create a game in a graphical style environment with their own programming language and to generate output that cross-compiled to all those target platforms. It sounds like a fantastic solution, but I don't think it was beloved by the developers who used it because they referred to it as scum. But scum did work. And it addressed all the target platforms that they had to do. And in fact, you can still run Maniac Mansion today in Scum VM, which is an open source project. And all the games that they wrote for it continue to work to this day. Now, if we look at the economics behind this, what the team had to do was decide whether or not it was cheaper to write an application for the Commodore 64 and then port it, essentially rewrite it for every single other platform, or whether or not it was cheaper to create the runtime, write the game for the runtime, and port the runtime to all of the available platforms they had to support. And if we look at the balance of scale, the Scum Balancing Act here, it was indeed cheaper for them to go and write this engine. And it's kind of similar to what we do with WebAssembly today. So I work predominantly in the embedded world. And if we're doing WebAssembly today, here's a bunch of WebAssembly, here's a bunch of real-time operating systems we need to support. And that's just the operating systems. When you take into effect the different chipsets and architectures, there's roughly 6 for each of these, so it's quite a plethora of different platforms that need to be supported. And going back to our balancing act again, you know, it's basically the same thing. It's the same economics, right? It makes sense. Or does it? It should do. But what I want to talk to you today is about where things differ and where there might be problems and what we can do about it. And to start with, let's look at how WebAssembly and its a process for approving new features works. You go from a proposal at stage 0 to a ratified standard at stage 5, but perhaps the most interesting stage is 3, where you start to see implementations appearing in the major browsers and tool chains. Now for us it kind of looks like this. You get a Firefox and Chrome implementation in Scripton with the probably the chosen compiler architecture for WebAssembly for the web. Eventually, the Inscription team might upsource stuff to Clang, and it gets pulled down into the WASI SDK, and then you get access to it, which is where we are in the embedded space, mainly in the WASI SDK. But there could be multiple proposals all going through this process at the same time. And what does that mean for us? Well, let's imagine I'm going to create an IoT device that looks a bit like Thor's hammer with a couple of aerials stuck on the top. And I've got a ROM image, and I put my WebAssembly runtime on the ROM image. And I know my runtime supports features A, B, and C. Everything's great. I get the latest Clang. I build my C code, and it works. It's fantastic. And that's because my runtime features match my compiler features. But in the standardization process, when you get to stage 3, features are enabled in the tool chain as experimental and default off. When they get to 5, they're often default on. So at some point in the future, when I go to build my next update for my application, I do the same thing. I go to the web and I pull down the latest Clang and I go and build it. But now I'm getting features I didn't want turned on, features that my runtime doesn't support. And when I go to run my code on that runtime, it doesn't work. This happened to us with reference types. So let's go back to our scales again. What does this mean? This means I have to do all of this work, plus now I need to maybe maintain a compiler, or at least be aware of what's going on. There's some additional cost I have to take on board because I'm using WebAssembly. Now, often I'm not just building applications using the compiler directly. I'm using WASI, and specifically WASI Preview 1 without the component model at the moment. But I want to use that library. It's very useful. And I would do the same thing. I would just go to the web and pull down the pre-built releases and use those to build my applications. And that should work, right? So I'm managing my compiler. I just pull down the latest releases. I build my stuff, and I link them together, and everything should just work. Except, how does the WASI libraries get built? Well, they get built with the latest Clang. And so it's introducing instructions and opcodes that I don't support in my runtime. And when I link everything together, it just doesn't work. Sometimes the WASI development team turns on additional features that benefit the creation and the maintenance of WASI. And one of those was including debug information. And the result of that was that Hello World jumped from 4.5 kilobytes to nearly 50 for an embedded device. And I've not changed my compiler instruction here. My way I invoke my compiler is exactly the same. So the way I have to solve this is now I have to go and build my own sysroot. So now I'm maintaining a compiler and building a sysroot, and these are the costs I have to carry if I'm going to use WebAssembly. And so I look at my scale and I add an extra weight. But software, unlike Scum, the software we're using in WebAssembly, it doesn't exist in isolation. We have other things. We have a huge open source community and a lot of open source software that delivers an awful lot of value. And the Harvard Business School did a report they released in 2024 that said that open source software, to rebuild the open source software that we use most commonly today, would cost $4.15 billion. But that same software delivers to the economy $8.8 trillion of value. And for most development teams, if you had to recreate that additional software that you could use for free, it would increase the development cost by 350%. So having access to open source software is really important. And in the embedded space, we're mainly interested in C-based code, so not the entire set of this, but a huge chunk of stuff is written in C, and we would want to use that. And the most popular operating system for open source software is, of course, Linux, so that's kind of important. But if you go and try and build stuff, and here's a screenshot of what happens out of the box, things don't work. And there's missing features in our API. So our WASI API is kind of narrow. It's not as wide as it could be. And so we don't have access to everything. And we're missing some core WebAssembly features that would make it easy to bring in software. And that makes it difficult too. So if we go back to our scales, we can now add the cost of not having access to all of the software that we need and would like to use. So what can we do about that? Well, I'm involved in the Bytecode Alliance, along with Oscar and many others here. And there's a group called the Embedded Special Interest Group, and I help with that. And what we're attempting to do is create some long-term support. Essentially make sure that we get the latest security releases for the important toolchain artifacts and runtimes, and just make sure they're all in sync. The features just work, and they all work out of the box. So other developers, when they come to use this, don't have to pay the cost of maintaining their sysroot and compiler. It's a pretty straightforward proposal. Have a downstream copy, bring in the CVEs and updates, and make sure everything works. And if we did that, we could try and rebalance our scale a little bit and take some of the cost away. We still need to look at how we provide access to the open source software we'd love to use. And that's probably a process of the standardization process. You know, with our stuff, signal handling would be fantastic. It's a software interrupt. If I had that, I could do a lot of porting of open source software. Past example was set jump and long jump that was missing and gets re-implemented with exception handling. There are other things we would like from the system interface itself, and that's probably a question for the WASI subgroup. So there's some work we could do there too. Let's look right now at how the WASI subgroup works and what goes on with WASI, at least with Preview 1. The WASI group defines a standard set of API specifications, and then every runtime that wants to support WASI has to implement those specifications. And those APIs talk to an underlying operating system. So if you're running on Linux, if you're running on Windows, regardless of the runtime has to implement the same functionality, and it's a duplication of effort and cost. It's the same bit of logic that's going to connect a runtime A to Linux that will connect runtime B to Linux. So is it possible to break these apart? Is it possible to say, look, you just do the runtime, and we'll just deal with the system interface in a different way? And honestly, the inspiration of this comes from a lot of people in the room, Ben and Arjun, and some of the concepts from Carnegie Mellon in the WebAssembly Research Center. And could we break it apart? Could we say, look, runtime A and runtime B, they need to talk to Linux, they need to talk to Windows. Could we provide one binary that both runtimes could use that would provide that system level interface for them? And that would require a universal API for supplying plugins to WebAssembly runtimes. We don't quite have that at the moment. What we do have in terms of a kind of standard is the WebAssembly or the WASM-C API, which defines a common API for embedding runtimes into a host system. But what we really need is a plugin C API that would sit and allow us to bring in multiple system plugins. If we could do this, it would help us, obviously, and I think it would probably help our friends who are developing the component model too. So what would that extended system level interface look like? Well, for academic sake, and because the economics indicate it so, there was a talk from Anil yesterday talking POSIX bad, Linux good. Well, most of the software we want to run runs on Linux, so if we had something that looked like Linux, that would be really nice, wouldn't it? And there's a lot of reasons for that, right? It's becoming almost a de facto standard for development. We all have Windows subsystem for Linux. Apple's introducing containers, which is a Linux API. There's a FreeBSD, has its Linux binary API that exists. There are other examples for WebAssembly, like Wally from Carnegie Mellon, and most recently BrowserPod, which allows you to run some back-end for web development in a browser. So it would be really nice if we could do that. But we don't want to throw away WASI Preview 1 support at all. We still need to support applications that have been built to use it. And you could do this by putting a WASI Preview 1 module in here and just using it to supply the front-end interfaces. At the back end, it would talk to whatever system interface plugin we develop. So let's do a little feasibility study. Is this actually possible? So this started as a concept, and we said, look, could we actually ever do it? And we took Wally because not every browser, every WebAssembly runtime implements Wally. When we started, the only one that did it was WAMR, and that was through the work of Arjun, thank you very much, and Ben and the team at CMU. And we said, look, if we make Wally work on another runtime, it would be pretty binary. It would either work or not work. If we did WASI, we might have skipped something, and because everybody supports it, and it wouldn't be such a good test. Let's use Wally. So let's take Wally, and what we want to do is break it out from WAMR as a standalone library, and we want to make sure we can run it against 2 different runtimes. So we said, well, we'll relink it to a new version of WAMR that doesn't have Wally support, make sure that works, and then we'll use it with Wasm Edge. Just see if we can provide it as a plugin for Wasm Edge, and see if that would work. And so the binary, we take it out, it's about 120 kilobytes, unoptimized, it's not huge. And it worked. So with WAMR, we can invoke and run Wally-based, there's too many W's here, we can invoke and run Wally-based WebAssembly modules with WAMR, where WAMR doesn't have the Wally built in. So we can supply it as a native library here. You can see it from the command line. And the next bit was, well, that exact same native library, which supports a WAMR interface, could we then take it and get it to run with Wasm Edge? And Wasm Edge does not support WAMR native interfaces. Could we do that? And the answer is yes. So you can take the exact same binary. So could we reduce the costs of developing system interfaces by just supplying a common interface binary for the platforms that we want to support and allow any runtime that wants to use it to use it? And I think the evidence is there that this might be a feasible option. Now, it's not a perfect solution. This is just proof of concept and just an academic exercise just to show that we could do it, but it plants the seeds of where we could go. So let's go back to our scales again. Now, if we did this and we could provide support for Linux-like software, then we can really, really start to rebalance our scales and get back to where we were. Now, this might seem that I'm not particularly fond of some of the standard stuff, and I've been quite critical, and that's not true. Standards are really important, and the formal specifications of the standards are really, really great. They offer something that I think no other runtime really has at all. One of the problems we've been looking at in the embedded space is often our solutions want to be embedded into safety critical or certified environments. And they are very expensive environments to update and maintain software for. And there's this problem called mixed criticality, where you've got a safety critical system, but you want to run some non-safety critical code on it. An example might be an airline wanting to get metrics off a black box in the aircraft to see whether or not their pilots are doing the right thing. Could you do that? Well, not today, not without extra hardware. Just because it's so cost ineffective to update certified software and get it recertified, that what most people do is they just pay the cost of extra hardware, have 2 completely separate systems, and have a hardware link between the 2. This works, but it's expensive. If you could do it all in software, it would be cheaper. What if you could have a certified sandbox? And inside that certified sandbox, we can run our non-safe application, whatever it might be. Our metrics collection from our black box, metrics collection from a piece of machinery in an FDA-approved manufacturing process for healthcare equipment. That would be really important. Is it possible to do? Well, yeah, we've got SpecTech, right? We've got this formally specified runtime. We can verify, well, it's formally specified language. If we could do that, and if we could have a verified runtime and a certification authority that would take that and say, yes, we certify you could use that in a safety critical environment, or at least in our critical environment, whatever it happens to be. If we could do that, then we could have a cost-effective way of inserting non-safety critical code into that environment and solve this cost point problem. And that, in those environments, would really tip the scale. Now, I mentioned tuna head earlier. So where did that come from? the opening scenes of Maniac Mansion. The characters are debating whether or not they're brave enough to go into the maniac's house. And one of the lead characters says, well, if anybody wants to back out, you can do so now. And in the original plot, and the original script, the authors, a guy called Ron Gilbert, he really wanted his character one of his characters to walk out. The nerdy guy would walk out in fear. And the main character would call after him and say, don't be a, and I don't think I could say this at a conference, but it is a something head. You can take the first few letters of these words and work it out. And George Lucas is like, you can't put that in a computer game. You can't, we're going to sell this to kids on a Commodore 64 playing at home. They can't have swear words in them. So instead, it became, Bernard, don't be a tuna head. So that's my talk. Thank you very much.
Thanks so much, Chris. So plenty of time for questions. How do you feel about concurrency and shared everything threads?
So not in the talk, but a lot of what we're doing at Siemens is concurrent WebAssembly. So yes for concurrency and yes for shared everything threads, please.
Do you have a runtime that you would like someone to stamp, or do you think it would sort of need to be written fresh with certification in mind?
I imagine it would need to be written fresh with certification in mind. But I wonder if part of that could be mechanized. I don't know.
I guess you should talk with Sandrine, but I think she's attending another session. So.
Hi, thanks for the talk. I also have a question about certification.
Yes.
I was wondering what you had in mind there, because in industry, my understanding is there's a notion, well, and government, there's a notion of what certification means for software, and it is not probably what a lot of the people at this event would think of. Not formal verification, but sort of building lots of processes and testing frameworks and so forth.
Right.
What did you have in mind? Was that both formal verification and ISO, whatever it is?
Yeah, it would probably be, realistically, it's probably going to be a combination of the two. But what we've seen in this world is the German Aerospace Authority, DLR, working on a safe WebAssembly runtime. Not particularly fast, but safe. That would be really interesting. But there's different levels of safety certification. So there's safety certification for cars and for rail and for aerospace, and probably aerospace is one of the most challenging. And there's different levels of it. And what we're attempting to do is find out, can we talk to these certification authorities and find out exactly what they would need and what could we do with it? And I'm heartened by the work to get C++ compilers with formal verification working for Airbus. So maybe there's something we could do there.
Right, I mean, I'm thinking maybe something more tractable than what we might have in mind might be a good starting point.
Indeed.
Chris, thanks for a lovely talk. I liked your idea of a plugin for these kind of system-specific interfaces. Would that be useful for other language runtimes apart from WebAssembly, or should everyone just be targeting WebAssembly anyway?
sometimes don't need to implement anything except provide support for this interface. Thank you.
Great, thanks so much.
See.
Just while I'm waiting for you to have the speaker for the next talk. Just check you can advance. Wonderful. Great. So our next speaker is going to be my PhD student, so I promise no bias. But this is Antanas Kauskas talking about updating WASM-cert Isabelle to WebAssembly 2.0.
Yeah, hello, I'm Antanas Kauskas from Nanyang Technological University, Singapore, and I'm going to talk about updating WASM-cert Isabelle to WebAssembly 2.0. So the language standard of WebAssembly supplies pen and paper formal model of language semantics. And this formal model can be mechanized, that is encoded in interactive theorem provers. And those mechanizations can then be used to verify properties about the languages, such as type soundness, or to derive formally verified artifacts, such as type checkers and interpreters. And this has been demonstrated by the WASM-cert project. So WASM-cert project consists of two sub-projects. WASM-cert Isabelle, which is WASM mechanization in Isabelle Hall, and WASM-cert Coq, which is a mechanization in ROC. So WASM-cert Isabelle was the first WASM 0.0 mechanization, but since then it has been overtaken by WASM-cert Coq, which was the first to mechanize WASM 2.0. Still, WASM-cert Isabelle has been previously extended to cover some of the extensions of WASM 2.0, such as SIMD and multiple value proposals. And now it has just been fully updated to WASM 2.0, which is the topic of this talk. And the main tasks to update to WASM 2.0 was to extend WASM-cert Isabelle to cover bulk memory operations and reference types proposals. So the update touched most parts of WASM-cert Isabelle, including definitions, which include typing rules, reduction rules, and other language structure, the type soundness proof, verified type checker, interpreter, module checker, and instantiation procedure. The added bulk memory proposal, it introduced new instructions for bulk memory operations, such as memory copy and memory fill, which are similar to memcopy and memset functions from the C standard library. It changed the module structure, in particular element and data segments, which are used in the instantiation stage, and it changed the instantiation procedure. Reference types proposal introduced new value types, funcref and extendref for references, new instructions for manipulating the reference values. It modified the type checking procedure, and it modified the type system, and it required a large refactoring for the type soundness proof. So a bit about the changes to the type system. So in WebAssembly, instruction sequences are typed by stack type, which consists of a tuple of lists of operand types, which represent
what kind of values are being consumed and produced on the stack. The operand type can be either a value type or a bottom. So this bottom type has been introduced in WASM 2.0. One of the motivations for introducing that was to simplify the type checking procedure of unreachable code, and this bottom type can only arise in typing unreachable code. And there is a subtyping relationship for operand types, so that relationship is reflexive, and the bottom is a subtype for any other type. WASM 2.0 spec contained some bugs in defining typing rules for instruction sequences. Those bugs were spotted previously in WASM set-cock, and we implemented a corresponding fix, which is also a similar fix as in WASM 3.0. So one part of that fix was introducing subtyping rule for stack types. And also, here are the rules for typing of instruction sequences. So the subsumption rule, it is a rule that uses that subtyping rule of stack types, and it replaces previously used weakening type rule. Now, a bit about the metrics of the code change in the mechanization. So overall, the mechanization grew from 20,000 lines of Isabelle code to 27,000 lines of Isabelle code, which is an increase of roughly a third. Significant changes were needed for type soundness, type checker, interpreter, and instantiation. One thing to note is that the type checker actually, the type checking procedure got simpler, and like the number of lines for the type checker definition and the soundness proof actually shrank, even though the language expanded. Now I'm going to talk about optimizing the verified interpreter, which is, well, one part of the mechanizations. So in the mechanized language semantics, WASM memory is represented as a linked list of bytes. And to specify stateful operations that mutate the memory, there are two functions used, memrep write bytes and memrep read bytes, which are defined in standard functional list functions such as take, drop, and append. So an interpreter does not necessarily have to use the same representation and the same functions to model WebAssembly memory. But if you want to verify it, perhaps the easiest way is to remain close to the semantics and use the same representation. So for instance, if we use the same representation of memory, the flow for i32 store instruction could be simplified in this way. Well, we pop a constant and an address from the stack, we serialize the address, and we write the serialized bytes to the address using memrep write bytes. And in the extracted OCaml code, the memories are expected to the list. The issue is that, well, this is inefficient because these memory access operations on the functional list, they have linear complexity in the address. So then the question is, can we make the verified interpreter more efficient? Because, well, we would expect memory mutation procedures have roughly constant complexity. And one way we could do this is to use a different OCaml data structure for memory representation. So one of the structures is OCaml bytes, which is a mutable data structure for sequences of bytes. But since it is mutable, for the extraction to be sound, we have to model the mutability, like the verified interpreter has to model that mutability. This has been previously done in WASM-Ref Isabelle project, which took WASM 1.0 together with SIMD extensions and made a verified monadic interpreter that had this state monad for the memories. But this made the interpreter more complicated, more difficult to maintain, and well, it requires additional verification effort. So then the question is, maybe there is a data structure that has similar interface or similar semantics as immutable functional lists, but it has maybe better performance for our use case. And well, yes, there is one such data structure. It's persistent arrays, which is a persistent data structure that has been previously used in Wasm-Sert-Koch mechanization to optimize stateful operations. And now I'm going to explain a bit what is a persistent array. So p-array basically wraps a single mutable array, and it can have multiple nodes which represent different versions of that array. So each node could either point to that single version of a mutable array, or it could point to a different node together with the information of the difference between the two nodes. So on the left we have some pseudocode for manipulating p-arrays. So we initialize a node x, which points initially to the list of array of size 5 of characters A, and then we can define y to be a modification on x, and then, well, x does not point at the array itself, it points towards y. So this means that x is the same as y, with zeroth position being replaced by character A. We can further define z in terms of w, and we have a different graph. And moreover, we can define w, which is not defined in terms of the most recent version of the array z, but it can be defined in terms of an older version, and then the graph is being rerouted. So now we have 4 nodes, and we have this graph of differences between the nodes, and all of these nodes, in principle, all of these nodes can be reconstructed if they are needed. And this data structure is perhaps the most efficient when you are most of the time accessing recent versions of the array. And yeah, we can use p-array and extract memrep write bytes and memrep read bytes to use p-array set and get functions. But the issue is that the default interface of p-array only allows manipulating a single element of the array, so it only allows byte by byte memory manipulation. So a simplified flow of I32 store could be, well, we pop a constant C and an address, serialize it into the bytes, and then we iterate through the byte list, setting each byte one by one into the memory. Yeah, but most of the operations in most of the memory operations in WebAssembly operate multiple bytes, so p-array could be inefficient. To address this, we implemented a persistent data structure on top of OCaml bytes. So this data structure has an interface for manipulating multiple bytes at once, or multiple integers of different widths. So then, if we have a function memrep write I32, which uses p bytes set in 32, then the flow of a store instruction could be, well, we pop a constant and address from the stack, and we write it into the memory using p bytes interface. Well, and this requires fewer machine instructions. Now, there are some further ways that we can could potentially optimize the interpreter, and one of the bottlenecks that we spotted was the bulk memory operations. So in the semantics, the bulk memory operations could potentially push multiple values and instructions to the stack. And we have, to illustrate this, we have this memory fill, the semantics for memory fill operation. There are 3 cases. So the first and second case are maybe less interesting. In the first case, well, this is the trap case in case we try to fill memory outside the bounds. In the second case, well, the instruction sequence terminates because, well, we are trying to write only 0 bytes. The third case is the most common case. If we try to write n+1 bytes, so I mean more than 1 bytes, there are instructions issued to write a single byte, and then there's another instruction sequence issued to write the remaining bytes into memory. And the interpreter, since it follows those semantics closely, it kind of also performs these kinds of pushing of multiple instructions to the stack. Well, it could be obviously optimized to implement the bulk memory operations actually in bulk without pushing the instructions to the stack, but, well, the issue is that it would require a significant refactoring of the interpreter soundness proof, as right now it heavily relies on one key lemma, and it is one of the most difficult lemmas to prove. And that lemma, well, says that a single step in the interpreter corresponds to a single reduction in the language semantics. Now, we also have some benchmarks for running the WebAssembly reference interpreter and Wasm set Isabelle interpreter with different interpretations of different representations of memory. So if we run this on Wasm 2.0 test suite, the reference interpreter is the fastest. Wasm set Isabelle with p bytes, well, is 20% slower, and well, Wasm set Isabelle with list takes a reasonably long amount of time. Well, if we exclude some tests that utilize heavily the bulk memory operations, we actually can get Wasm set Isabelle to be faster than the reference interpreter. Yeah, and for conclusion, well, Wasm set Isabelle now fully covers Wasm 2.0. So far, Wasm set Isabelle has been a handwritten mechanization, and you saw how much effort it takes to update it, even though like Wasm 2.0 is a smaller extension compared to what is going to be Wasm 3.0. So we hope that update to Wasm 3.0 and further maintenance effort would be aided by SpecTech. We investigated ways to make the verified interpreter faster or try to check what are the main bottlenecks. And well, to speed up the interpreter, we implemented p bytes data structure, which is a persistent data structure built on top of OCaml bytes. And Wasm set Isabelle with this achieved a comparable performance with the reference interpreter, or beating the reference interpreter if we exclude bulk memory operations. Yeah, that's all.
Great, thanks so much. Questions for the speaker?
Thank you for your talk. So can you quantify, like in terms of person years, how much is the effort for you to upgrade from Wasm 1 to Wasm 2? Well, you showed the number of lines, but...
Okay, so it's probably a few months. It's like 3 or 4 months, maybe. Yeah, I would say 3 months. That's that was the effort for me to update, yeah, to incorporate bulk memory operations and the reference types proposals.
Okay, and my second question was that, like, it feels that your P array or P bytes is a bespoke optimization for like a certain sort of operations that you need to do in Wasm 2. So I was wondering, like, how much in that perspective, like, SpecTech can help, because well, SpecTech doesn't really generate an optimizing interpreter, and
so SpecTech, there are many parts of the mechanization. Interpreter is maybe just one of them. SpecTech could definitely generate definitions. Perhaps something bespoke would have to be built on top of Spectre to optimize the interpreter. Like if we wanted Spectre to emit a fast verified interpreter.
Cool. Thank you.
Okay, I have a question. Which instruction did you spend the most time on in the type soundness proof?
So it's probably some of the bulk memory instructions. So memory fill, it's comparatively simple. Maybe memory copy, it took a long time, because there are maybe 4 cases and they're pretty long. Yeah.
Yeah, for reference, this is because we decided we wanted to specify that depending on whether the destination or the source address is bigger, you copy in an opposite direction to make it unobservable, which means you have twice as many cases to handle. Okay, let's thank the speaker one last time.
Can I get
So our last speaker is Dinghong Zhong, and he's going to be talking about efficient concolic execution for WebAssembly by compilation and snapshot reuse. Please take it away.
Okay, thank you. Thank you for the introduction. Thank you everyone for coming to my talk. And I'm Dinghong from Tufts University. Today I'm going to present our work on efficient concolic execution of WebAssembly by compilation and snapshot reuse. And this work is done in collaboration with Alex from New York University and my PhD advisor, Guan Nan. WebAssembly is a low-level IR that can be run in various environments. It has been widely adopted in many important areas. More interestingly, it has a formal, well-defined semantics. It's interesting and important because it brings new opportunities for the semantics-based applications, such as semantics-based testing, static analysis, and verification. And today, we're focused on the semantics-based testing technique called concolic execution. In this work, we present an efficient WebAssembly concolic execution engine that can generate test cases to find bugs in WebAssembly program. And its performance is achieved by 2 optimizations. First is that it has no interpretation overhead. And the second is that it avoids the duplicated execution during the concolic execution. These 2 optimizations cannot be applied together in the previous works. And in the rest of this talk, I will discuss how to achieve these 2 optimizations at the same time. Concolic execution is a technique based on symbolic execution. Let's see what symbolic execution is with an example. Then we come back to the concolic execution. On the left is an example program that has 2 variables, x and y, which are assigned from 2 inputs. And it has an assertion error as its third branch. On the right side is all possible execution paths of it. We can feed this program to a symbolic executor and ask it to generate a test case that can reach the assertion error. First, the symbolic executor will replace the input of the program with symbols. Instead of executing the program with concrete semantics, it uses these symbols to execute symbolic semantics. During the symbolic execution, it will collect a set of constraints represented by these symbols. These constraints are called path conditions. They represent the condition of input that must be satisfied to reach a particular path. For example, the path conditions of the leftmost path is x less equal than 0, because to reach here, the first if condition must be true. Unlike concrete execution, symbolic execution can execute multiple paths of the program at the same time, just by executing the symbolic semantics for different paths and collecting the path condition for each of them. And we say symbolic execution is exploring the program. And we can see that the explored path of the symbolic execution naturally forms a tree structure called exploration tree. And using a constraint solver to solve the path condition can produce an input that reaches the path. For example, for the path that contains the assertion error, solving its path condition can generate an input that triggers the error. That's the basic idea of symbolic execution. However, there's a scenario which is challenging for symbolic execution. If the program contains some very complex logic at the beginning, right now you only want to focus on the deeper places of the program, and using symbolic execution found the bugs in there. The symbolic executor will spend a long time at the beginning of the program exploring the complex logic in there before reaching the part you really care about. To help the symbolic execution to reach the deeper path earlier, concolic execution comes. Concolic execution can be seen as a special exploration strategy of symbolic execution. It executes symbolic semantics on different paths, just like symbolic execution. But in concolic execution, the exploration is guided by concrete execution. That is why it's called concolic execution, because it needs to execute both concrete and symbolic semantics at the same time. Let's go back to the previous example to see how it works. First, concolic execution will start the program with a concrete input. Then it will execute the concrete and symbolic semantics at the same time. And in practice, this concrete input can generate it by a fuzzing tool. So it can start the exploration from a very deep path at the beginning. After the first run and no error was triggered, it will keep exploring the program with different input. When it catches an error in the program, like our example here, it successfully generated a test case that triggers a bug, which is just the current concrete input. That's the basic idea of concolic execution. It can reach deeper places earlier just by starting the exploration with a concrete input that reaches the deeper places. There is an interesting thing that you may have noticed. During the concolic execution, different paths are sharing a common subpath. For example, we have explored the first path, which is marked in green. And now we want to use a different input to explore a new path, which is marked in blue. You can see that the blue path and the green path is sharing a common prefix. And the execution of this common prefix is duplicated. When the execution goes deeper, the cost of such re-execution could be significant. Ideally, to avoid such re-execution, when exploring a new path, we should start from the end of the common prefix, rather than start from the beginning of the program. To do so, we need to save a snapshot of the program, where a snapshot is the control information and the symbolic states as the branch points. When concolic execution wants to explore a new path, it can reuse the snapshot, resume the execution from the snapshot, and avoid re-executing the common prefix. And this reuse mechanism is called snapshot reuse. That's the basic idea of concolic execution and its snapshot reuse optimization. For the implementation of concolic execution, there are two main patterns for the mainstream works. The first one is interpretation-based approach, and another one is instrumentation-based approach. And they both have their own pros and cons. Let's see them one by one. Since the concolic execution is guided by concrete execution, a straightforward way to implement it is to base the implementation on an existing interpreter. Inserting those extra symbolic operations into an existing interpreter to turn it into a concolic interpreter. Running this concolic interpreter will not only get the concrete output, but also the path conditions collected during the execution. For example, the work WASP in 2022 eCoop do concolic execution for WebAssembly by inserting extra symbolic operations into WebAssembly official interpreter. For this approach, snapshot reuse is not a challenge because the control information and the states are fully managed by an interpreter. However, for the interpretation-based approach, there is an inherent performance limitation. That is the interpretation overhead of dispatching on different instructions. It's a well-known limitation of interpretation, and lots of work have shown that this overhead could be significant in practice. A solution to the interpretation overhead is implementing concurrent execution by instrumentation. Instrumentation is a program transformation technique that inserts extra operations into the program to collect hidden information of the program during its execution. If we treat the past conditions as the hidden information we want to collect, we can build a concurrent executor via instrumentation. Here is an example for the instrumentation for IR/VM/IR. We can see that the symbolic operations have been inserted at the head of the program. When the execution reached here, these symbolic operations will be executed first, then comes to the original concrete instructions. In this way, we achieved concurrent execution for IR/VM/IR. This is not a WebAssembly example, but it's not hard to apply the same idea to the WebAssembly concurrent execution. If we build concurrent execution in this way, it will have no interpretation overhead. However, at the instrumentation time, the program doesn't capture the control information, therefore disables the snapshot reuse optimization we just talked about, because snapshot is created from the control. That is why we want to have a new approach that can combine the best of these two worlds. First, it should have no interpretation overhead like instrumentation-based approach. And it should be able to do snapshot reuse optimization to avoid re-executing the common prefix like interpretation-based approach. To achieve these two goals at the same time, our idea is compiling the WebAssembly concurrent semantics to a low-level program language with continuations. To capture the control information, our approach is based on the CPS semantics of WebAssembly, which was proposed in our previous work on TFP'25. To do concurrent execution, we first insert extra symbolic operations to CPS interpreter to get a concurrent interpreter. To eliminate the interpretation overhead, we apply the partial evaluation to the staged version of CPS concurrent interpreter to generate C++ code. Finally, combining the generated code with the runtime of symbolic operations, we can get an executable concurrent program. This concurrent program performs both concrete and symbolic semantics and uses captured control information to achieve snapshot reuse. Now let's get into some technical detail of our approach. Our compilation is based on a program transformation technique called partial evaluation. It takes two inputs, a staged program P and P's input that can be known in advance, called static input. The output of partial evaluation is called a residual program. In residual program, there is no more computation that only depends on the static input because they have been pre-computed during the partial evaluation. Staged program is just a normal program with some binding time annotations, which is just a type of annotation indicates whether an expression depends on static input or dynamic input. The lightweight modular staging, LMS, is a partial evaluation framework embedded in Scala. We use LMS to apply the idea of partial evaluation. Let's see how LMS works with a simple example. Here on the left is a function that computes b to the power of x. When the exponent x is known in advance, we can specialize this function respect to x. So we mark b as dynamic input with wrap and leave x as it is. In this way, if we apply partial evaluation to a specific x, for example, if x equals to 2, then we can get a specialized version of power function in C++ that only takes b as input and calculates b squared. Remind that the residual program is in C++. This is a powerful feature of LMS. It can specialize the staged program into different languages. The application of partial evaluation can be very flexible. If we apply this technique to an interpreter, partially evaluating the interpreter with the source code as the static input, we can get an executable program as a residual program. This observation is also known as the first filter mirror projection. And we will realize this observation to implement our concolic compiler, partially evaluating a concolic interpreter with the WebAssembly source code to get an executable concolic program. Here is the outline of the staged concolic interpreter. It's a staged version of a concolic interpreter with several parts are marked as wrap, which represents the dynamic computations. First, we use function without parameters to represent continuations. The eval function contains the core logic of the interpreter. It takes a list of instructions, a continuation, and a trail as parameters. Based on this captured continuation, we can create a snapshot further. And the trail is a list of next stage continuation, which acts as local jumping tables. On the other hand, the instruction list and the trail parameter are not marked as wrap. So the computation based on them will only exist in the current stage. For instance, the instruction dispatching expression in the eval's body are all happening in the current stage. So they will not occur in the generated code. In other words, the interpretation overhead is eliminated. Here is the compilation for some simple instructions. For the const instruction, we push a constant to both concrete stack and the symbolic stack. Correspondingly, in the generated code, there will be two push operations. And for the BR instruction, which stands for branch, we enter the continuation stored in the current trail. And in the generated code, there will be a function call to the continuation function, corresponding to the label 1, which is x3 here. And another interesting example is the compilation of if instruction, because it shows how we utilize the control to achieve snapshot reuse. Here on the left is an example of if instruction, and on the right is the generated code of it. The generated program first pops the value that represents the condition from the concrete stack and the symbolic stack, and updates the exploration tree with the symbolic condition. And then use the concrete condition to decide which branch to go. If we enter the true branch, first we create a snapshot with the fourth branch's continuation and current symbolic states. Then we expand the exploration tree to the true branch and store the snapshot into the tree. Finally, we enter the continuation of the true branch. For the fourth branch, we just do the similar things. Create a snapshot, expand the tree, store the snapshot, and enter the continuation. That's the basic idea of implementation. And here's a preliminary evaluation of our concolic execution engine. We compared our engine with WASP, which is a concolic interpreter for WebAssembly in OCaml. The improvement by compilation is significant. On different configuration, our engine can achieve 6 to 15 times speed up compared to WASP. Once again, it's still a preliminary evaluation. The benchmarks are small programs that only last for a few seconds. And we are working on more comprehensive evaluation on bigger benchmarks. To summarize, we have presented a WebAssembly concolic execution engine that eliminates interpretation overhead by compilation to C++, and it avoids the re-execution via snapshot reuse. We built our compiler starting from a definitional CPS interpreter and realized partial evaluation to simplify the compilation. To the best of our knowledge, our tool is the first concolic execution engine that can achieve both no interpretation overhead and snapshot reuse optimization. That's all of my talk. Our source code is available at GitHub, and I'm happy to take any questions, comments, or suggestions. Thank you for your attention.
So this is a really cool work, by the way.
Thank you.
So it sounds like you kind of hack an interpreter to do the snapshot for you. So it's this combination of doing both interpretation-based and instrumentation-based. So is that correct?
It's correct, but we not based on the WebAssembly official interpreter. We developed our own concoding interpreter, and based on that, to do the snapshot and compilation.
So do you think that you would have a lot of, I guess there would be a lot of overhead if you do, because you could do snapshots inside instrumentation, right?
It's hard to do that because
be higher overhead.
You mean do snapshot in instrumentation?
Yeah, like do you think that it would be possible to do like the snapshots totally in instrumentation? It would be higher overhead, but you wouldn't have to have this custom interpreter.
I think it's hard to do that because usually at the instrumentation, the program doesn't capture the control. So.
Well, you could have like shadow memory and shadow stack and stuff to like.
You mean copy that would be a lot of
It would
hack.
be high overhead, but like, do you think that it would be so high overhead that it would be prohibitive?
That is not just overhead, but it's also not semantic based. So I'm not sure I'm answering your question, but our work is based on instrumentation on an interpreter, which is semantic based. So we can ensure the correctness during all the time. But if you want to do that via instrumentation, I think it's hard to ensure the correctness.
Yeah. Okay, we can talk more offline.
Yeah, of course.
Yeah, cool.
So, this is very foreign to me, so the question might be nonsensical, but I'm a little bit surprised that you start from a CPS interpreter, because one of the things that WebAssembly has, it has this sort of structured control flow that does give you this information. And then you seem to sort of immediately throw it away, because a CPS interpreter kind of forgets all of that structure in a sense.
WebAssembly's structured control flow only captures the local control information. And what we want to capture here is the full control information. So like what we are going to do after the function return. So.
Okay. Okay, thank you.
Thank you.
Thanks for the impressive talk.
Thank you.
I know when I used to have some similar things on LLVM, I'm not pretty sure it's the same thing or what was the difference. So what's the gap here between the LLVM stuff and here for WebAssembly?
You mean what work on LLVM?
I mean, when I used to have the version on VM, right? Is it the same thing or?
The essential idea are similar. It's about eliminating the interpretation overhead and utilize the control of the program. So it's definitely not the same thing because the language is different. But I think the basic idea is really similar. Yeah.
Nice. Thanks.
Great. Let's thank the speaker one last time.
Thank you.
Thank you, everyone. So with that, we have reached the end of the WebAssembly workshop. Thank you so much for sticking with us. Next year, we will not be running a WebAssembly workshop in Popple, because I think another WebAssembly workshop in 2 or 3 months' time would be a little too much stress on the community. But I do aim to propose one for the next again, Popple. But thank you all for coming to this one. In previous WebAssembly workshops, I've tried to end with some kind of dinner announcement. Unfortunately, today I'm not available this evening, but I encourage you, if you've become passionate about WebAssembly and you've met other people you want to spend more time with this evening, please make your own dinner plans and include as many people as possible so that we can continue talking about WebAssembly until the next workshop in a year and a little bit. So thank you all for coming and see you at some point in the future.